Welcome everyone to the SIGGRAPH 2021 course on neural rendering. This course is based on the state-of-the-art report on neural rendering of Tevari et al., which was a great collaboration between multiple different institutions. We have an amazing set of speakers from many different organizations, covering topics such as generative adversarial networks, novel view synthesis, learning to relight, compositional scene representations, free viewpoint video, facial and body rendering, open challenges, and ethical implications. We will end this course with a panel discussion and answer all of your questions. Currently, there are two alternative approaches for generating realistic synthetic imagery: computer graphics and generative machine learning. Both of these approaches to image synthesis come with unique strengths and weaknesses. For example, to render highly realistic images using computer graphics, we require high-quality assets, which require a lot of work to generate. On the upside, in computer graphics, all scene parameters, such as the light position or the camera position, are fully controllable. On the other side of the spectrum, generative machine learning techniques require lots of training data to learn the models. But if we have the training data, we can learn the 3D representation automatically without having to model it. One other downside of such approaches is that there's no fine-grained control of the scene parameters I mentioned. So fusing these two paradigms leads to a new class of approaches called neural rendering approaches that allow us to get the best out of both worlds. For example, creating photorealistic assets is challenging using classical computer graphics techniques. One reason for that is that the real world is highly complex. For example, as you can see here, many real-world objects contain transparent surfaces. They are glossy. They have thin structures. And if we look at humans, they are also highly complex. For example, the human skin shows subsurface scattering effects. We have a large variety of appearances in terms of different clothing. And if we look at the human head, it's a combination of all of these effects. We have fine scale structure in the human hair. The teeth are specular, the eyes are specular and transparent, and all of that comes together and makes it so hard to model in a classical manner. Neural rendering can be used to learn such photorealistic assets from image data. And actually, all the images shown here are not photographs. They are actually neural renderings produced by the approach of Lombardi et al. Let us now define a bit more in detail what we mean with the term neural rendering. So we mean deep neural networks for image or video generation that enable explicit or implicit control of scene properties. So as you can see, this definition has three parts, and there needs to be three components for a neural rendering approach. First, we are interested in generating images, so we are interested in generating raw pixel output. The second aspect is controllability, so we want to control which images are generated. The third aspect is that this control comes in the form of physical parameters we can control. For example, where the camera is, what the illumination is, how the geometry is shaped, and so on. Let us now have a closer look at the core idea of neural rendering. Classically, computer graphics is starting with a 3D scene description in the form of a definition of where are the light sources in the scene, what is the geometry, what are the materials, what is the motion of the geometry, and where's the camera placed. From this, computer graphics tries to render realistic 2D images. And this is the CG function you can see here. We have a scene as input, and we get out an image. Machine learning normally works in the opposite way. Starting from a training corpus of 2D images, we want to learn something about our physical 3D world. We can now put both of these paradigms together and close the loop. For example, we can learn a computer graphics inspired 3D scene representation and potentially also the rendering function from the 2D observations. This joint learning problem and augmenting the network with computer graphics inspired inductive biases for better generalization is what neural rendering is all about. Let's now have a high-level look at the zoo of neural rendering approaches and the network architectures that are currently out there and frequently used. This list will not be exhaustive, but covers many familiar designs and patterns you will find later on in the other talks. The first neural rendering techniques were basically working as shown here on the slide. You have a 1D code that, for example, represents where your camera is located in a scene and in which direction it is looking. And you feed that to a 2D generative network that directly outputs the corresponding image. The downside here is that learning this function from, let's say, the camera position and camera orientation to the raw pixel data of the corresponding image is highly complex, and such approaches thus need really a lot of training data if they want to generalize to new camera positions. For better generalization based on less training data, the next class of approaches makes use of actual computer graphics. So here the idea is that you start from a classical computer graphics representation, for example, a 3D mesh or a 3D point cloud that describes the scene you're interested in, and optionally you also tag some codes to the 3D representation in 3D. And then, let's say you want to render a novel view. What you do is you use classical computer graphics to first render the mesh or the point cloud to the new view. And if you have these codes, you can also use the same function to render these codes to the novel view. So you end up in 2D screen space, and you have a feature map in the 2D screen space. And then you use a neural network to convert from this feature map to a color image. And there are many techniques, for example, deep video portraits works like that, or deferred neural rendering works like that. The third class of approaches swaps the computer graphics component and the learning component around. So this class of approaches first starts with a learning-based part, where you take a code that describes your scene and then you pipe it through a learned neural network that would actually output the computer graphics representation. And that can, for example, be a 3D mesh with a 2D texture map on top. This could be a colored 3D point cloud, or this could be a volume of color and opacity data. Finally, after generating this computer graphics representation, an actual computer graphics routine, which is normally not learned, is used to generate the final 2D image. And an approach that works like that is, for example, neural volumes. The last class of approaches kind of builds a sandwich out of the computer graphics and machine learning components. And one approach that works like that is NeRF, neural radiance fields, which is currently super popular in the community. Here the idea is that you first do something classical. You use a classical computer graphics approach, for example, ray marching, to generate 3D sample points in space. Then for each of these sample points, you positionally encode the coordinates of that sample point. You run them through an MLP that outputs you color and opacity. And then along the whole array, after you obtain the color and opacity for all the sample points, you use another computer graphic technique. Here in this case, some volumetric aggregation scheme, which is basically alpha blending, to blend together all these colors based on the opacities and generate the final pixel color. With this, we are at the end of the introduction. Keep your eyes open for the 4 architectures that we talked about. I'm sure you will spot all of them during the next few hours. I hope you will enjoy the rest of this course on your rendering.
Hi everyone, welcome to the SIGGRAPH tutorial on neural rendering. I'm Junyan Zhu, assistant professor from CMU. I want to talk about a few why did you use loss functions for neural rendering. Let's take this sketch to photo as an example. Here, input image is X, and I would like to train a network G to generate output image G of X. And so here is the formulation. It's very simple. You have input information of the object X. This X can be a sketch, but it can also be your albedo map, texture map, or normal map, or depth map of some 3D thing or objects. It can be a semantic label map of the scene layout. It can be anything which describes this object and describe a scene you would like to render. You pass it to a generator. Again, this generator can have various forms. It can be a convnet. It can also be a MLP function, which used in implicit function modeling. It can be a transformer, which are quite popular now. It can also be a physically based differential rendering algorithm, but it can be anything which can turn some input information of the scene to output image. And it can be anything which are differentiable and can generate image. And this output can be an image of cat, but can also be image of a room. Outdoor images can be any kind of images. So regardless of what kind of X and Y you are working with, regardless of what kind of generator you like to use, you have to design a loss function L to train this network. And so this loss function might require some of our attentions. So the question we'd like to ask in this talk is, what is a good objective function to train networks for neural rendering tasks? We may agree that this loss function should capture some notion of realism. This should tell whether the output looks realistic or not. Maybe this function should tell whether output correspond to the input or not. Let's say I want to draw a cat. Even output is a realistic dog, but this is not what I want for this particular input information. And maybe hopefully this loss function can be useful for different tasks. We can use the same loss function for different tasks, and this loss function can adapt to a different task and different data sets. So let's start with something simple. Let's look at L2 regression loss. Given input sketch X, you have a generate G, and this loss function captured L2 distance between output G of X and ground truth image Y. And if you use L2 regression, oftentimes you get very blurry results. Why is that? Because there are multiple plausible outputs given the same input sketch. And the L2 distance tends to average the results together, try to create average images of all the plausible answers. And this is not what we want for most of the applications we care about. We do not want blurry results, kind of average color for the colorization. We do not want blurry results for super resolution, which is particularly bad because super resolution try to generate something which looks sharp. The researchers has proposed different ideas to address these issues. Some paper like Zhang et al. They proposed to write down colorfulness term, which encourage results to look more colorful. and other people have used so-called perceptual loss, which try to capture distance between two images in the deep learning feature space. So let's look at take a close look at this perceptual loss. So the idea is instead of calculating the distance in pixel space, we can calculate the distance in feature space of a deep network, and hopefully the feature space is more perceptual compared to the pixel space. So here is a generic image of g of x. Here's the ground truth image y, and you can use a frozen pre-trained network f to extract some features. You can extract some features, and you need to normalize the features, and you can calculate the difference between two feature vectors. And you normalize that difference, and then you need to average the distance at different spatial locations. And that's so-called perceptual loss, or some people like to call it feature loss, some people like to call it content loss. There are different names for the same loss, but it's implemented in the same way. And you may ask, why do we call it perceptual loss? How well do a perceptual loss describe a human perception? A recent study by Zhang et al. Found they have pretty high agreement with human perception of patch similarity. You ask some humans to determine which patch is closer to which patch, and machines agree with humans' judgment at 75% of times. And so this loss is particularly very popular, made popular by style transfer application, which you can add a perceptual loss between the output, stylized output, and input image. And it's also being used for semantic label map to photo applications, which you can calculate the difference between input image and a ground truth image. But you may ask, wait a minute, all we need is to mimic the human perception. Why not we just ask humans to annotate the data? So we can generate a bunch of images. We can ask humans to tell whether this image looks realistic or not. And we can learn a generator or a network from this human annotation. It's plausible, but it will be very expensive, and because the annotation, it needs to annotate not only the final model's output, you need to annotate every single output image during the training time. So if your training time have 500K iterations, you need to annotate 500K multiplied by the batch size of images, which are very expensive to annotate. So one idea is to replace this annotation with computer vision classifier. You train a classifier to classify whether this looks real or fake automatically. So you can avoid human annotation by replacing this annotation step with a classifier. And this idea was first proposed by the papers called Generative Adversarial Networks, or GANs, proposed by Ian Goodfellow and his collaborators. The idea is pretty simple. So here is you ask a generator to generate a photo, and you train a classifier to classify whether this photo looks real, which you predict a high score 1, or fake, which you predict a low score 0. And it's a two-player game, adversarial game. G tries to generate pretty images which can fool the discriminator D, while D try to be smart and try to detect fake images. And so here's how the math works. It's a very simple closed entropy loss, which for the generated images you want to predict a low score, and for the real image you want to predict a very high score, so that you can minimize this binary closed entropy loss. And from the generator's perspective, treat this entire two-player game to treat the discriminator as a learnable loss functions. So in the perceptual loss, we also use a second network F, but that network was frozen, does not adapt to the data. But here the discriminator is adapted to the data, to the task. But from the generator's perspective, the perceptual loss and discriminator loss is quite similar, because you don't care about how F or D was trained. The only thing you care about is this loss can tell you whether the image looks real or fake, and you try to improve your realism based on the discriminator's feedback. And you try to increase the score for your generated images to a higher score like 0.5, 0.6, and so that you can minimize your loss function. And but there's a small issue here is, for example, this image looks real according to the discriminator, but this image also looks realistic according to the discriminator. They both look real, but clearly you want the first input, you don't want the second input. So that's why we need to have two concepts. One is called realism, the other is called correspondence. We would like to generate a catch which corresponds well to the input image. To make it happen, we in the work of Pix2Pix, which done by Felipe Sola, myself, Ting Hui, and Alex Afros, we made a very small, kind of trivial modification, which will feed both the input and output image to the discriminator. The discriminator was asked to not only to tell whether the output looks real or fake, it asked to classify whether a pair of input and output is a real pair or fake pair. By enforcing this loss, you can generate something which corresponds to the input. And based on the ideal framework of Pix2Pix, our friend Chris has developed an online interface called Edge2Cats. Here is the Edge sketch. You can get a cat, and another sketch. You can get another kind of cattish kind of object. And here's how the interface looks like. You just draw something and you press the button, and you can get a cat photo several seconds. So you see it run on a browser. And here are more kind of creative or crazy cats from our artsy friends. But the interesting property of this adversarial loss or conditional adversarial Pix2Pix loss is it does not only work for sketch and photo. If you replace the input and output by grayscale image to RGB images, it can colorize the photo for use. And this loss will adapt to different tasks, adapt to different data sets pretty well. So this loss is a trainable loss function for the generator. But there's a limitation about this loss is training this kind of conditional adversarial loss requires lots of paired training data, such as edge to cats. I need to know which cats correspond to which edge in the training time. And in practice, these paired data are very expensive to collect. In many scenarios, it's not even possible to have access to a corresponding pairs. For example, if I translate a horse into a zebra. So the question is how we can design a loss function for this kind of generation task without access to the pair data. Of course, you can still use a discriminator loss to enforce whether this zebra looks like this output looks like a zebra or not. You can write down a discriminator loss by doing that. Either it's a real zebra or a fake zebra. But we try this loss alone, and it does not produce very good results. First of all, it produces artifacts. To make things even worse, it ignores the input and always produce the same output over and over again. And we need some additional constraints to enforce the correspondence between output and input. So right now the results do not look realistic, but also do not correspond to the input. And to enforce correspondence, we introduce a loss called cycle consistent loss, in the sense that if we translate a sentence from English to French, and if I don't know anything about French, one thing I can do is I can use the Google Translator to translate a sentence from French to English back, and I should expect to arrive at the same sentence as I start from. The same idea here. If you translate a horse into a zebra, and if we translate it back, we should arrive to the same horse as we start with. Here's how the math works. You have input image X, you have a generator G, and you translate it into domain Y, and you have an adversarial loss, which check whether this looks like a real zebra or fake zebra. But you also have then an inverse mapping F, which reconstruct this image into domain X again. And you can minimize this G and F simultaneously using an L1 pixel loss. And you do the same thing for the y to x to y directions. And here we go. We can make a horse into a zebra, another horse, another zebra, and you can learn the model like frame by frame. You can see some flanking artifacts. It's not perfect, but at least a horse or zebra is running. And you can translate the orange to apple. Another orange, you get another apple. Yeah, so the cycle consistency is great. It can enforce the correspondence and has been used in many different methods. And so the idea here is you would like to the inverse translation function is learned at the same time to minimize the pixel-based reconstruction loss. And the back translation should be penalized if they have different poles and if they have at different locations. However, the pixel-based cycle consistent loss also has some restrictions. It assumes bijection, which is sometimes too restrictive. For example, there might be many plausible horses that can correspond to the same zebra. But once the horse is transformed into a zebra, the color information is gone. And so therefore it shouldn't matter what color the back translation horse becomes. But apparently it matters for the current cycle consistent loss implementation, which shouldn't matter in reality. So you should be able to translate this horse to this zebra and should be able to translate to a different horse, but with the same pose, but maybe with different texture, maybe with different color. So we try to find a new kind of loss function which can enforce the correspondence while still have more flexible than the cycle consistent loss. Again, we translate a horse into a zebra. Again, we use a discriminator to make sure that the output looks like a zebra. But here we consider a pair of input and output patch at the same location like this horse head. And the idea here is we try to explicitly enforce that the embedding of this zebra head should be very close to this horse head. On the other hand, we would like to say that the patches from other random locations, like these patches, should be mapped to the embedding space into a location which are very far away from this zebra head. We formulate this using contrastive loss. So the corresponding input and output patches form a positive pair, while patches from other locations form a negative pairs. And in more details, we use cosine similarities. We maximize the similarity of the positive pair while minimizing the similarity of negative pairs. We try to pull these negative pairs far away from this zebra head. And we do this by formulating a classification task, which with the target label as 1 for the positive pairs and target label as 0 for the other negative pairs, like the patches from other locations of the same image. This loss is called info-NCE loss, was introduced and used in several recent works in self-supervised representation learning, such as Moco and Sinclair. However, unlike the Moco and Sinclair, which use handcraft data augmentation to create different positive pairs, negative pairs, here since we already have the outputs from the generator, we just form a positive pairs from the output of the generator and the input. We do not need to apply any augmentation. We have pairs which are formed by generator naturally, so it's perfect. And so to project the patches into the embedding space, we use the first half of the generator, to compute its embedding space. Embedding space is here. And we found that computing contrastive loss at multiple scales and multiple layers is critical for stable tuning because it can capture similarity at different scales. So in the end, our method can be a replacement of the L1-based cycle consistent loss. Our method does not require a second generator and a second discriminator in the inverse direction. And so our method is much faster in terms of tuning, requires less GPU memory, and this also enables a bunch of translation tasks such as cat to dog, summer to winter, or apple to orange, and different cities and GTA2 cityscapes. But now to summarize my talk, we introduce two kind of paired laws, like perceptual laws and conditional GANs, which both require paired data for the training. They can capture both the realism and correspondence. We introduce two different losses for unpaired training, which do not have input-output paired data. These only capture the correspondence between input and output. So oftentimes you need an adversarial loss, which capture realism. Due to the time limit, we do not have time to talk about other kind of wonderful laws, such as style loss, grammatrics loss, contextual loss, or maybe a domain-specific loss like face identity loss, or maybe 3D aware loss. By that, I want to thank my collaborators, and thank you for your attention. And for more details, please visit my website, as well as we have a new course at CMU, which talk about a bunch of other loss functions for generation tasks. Thank you.
Hello, I am Ayush Tiwari, and I will be talking about generative adversarial networks with 3D control. Generative adversarial networks, or GANs, are neural networks which take a sample from a prior distribution as input and synthesize realistic images as output. These networks are trained using datasets of high-quality images using adversarial losses. We have seen quite a lot of progress in the quality of images synthesized by GANs. For example, StyleGAN can synthesize very high-quality images at 1K by 1K resolution, so high quality as well as high resolution image synthesis. BigGAN can synthesize images of many different object categories. It is a class-conditioned generative model, and it is trained on the ImageNet dataset. While these GANs can generate photorealistic images of different objects, in neural rendering we are interested in synthesizing images with control over the scene properties such as camera viewpoint or scene illumination. While GANs by themselves do not have this kind of control in the image synthesis process, several recent methods have demonstrated that it is possible to expose 3D control in pre-trained GANs. I will talk about several such approaches in this part of the course. The common aspect of all existing approaches is a method to generate input latent vectors conditioned on 3D scene parameters. These methods figure out how to update either the input latent vector or some intermediate features of the generator such that the output image corresponds to the given scene parameters. Let's look at the first category of such methods, which uses supervised learning. PhotoApp, which we will present at the SIGGRAPH, uses a training dataset of portrait images captured under multiple camera viewpoints and illumination conditions. So we have pairs of images under different scene conditions. Now if we can project these images onto the latent space of StyleGAN, we can train a simple two-layer MLP network which transforms an input latent vector to the output latent vector conditioned on the target scene illumination and camera viewpoint. A simple loss function between the predicted and ground truth latent vectors can be used for training. For this method to work, we of course need a good projection function, and I will discuss this in more detail later in the talk. PhotoApp has some additional loss functions and design choices, but this is the overall high-level idea behind the method. I will do this for all methods I cover in this talk, focusing only on the main ideas. The simple method in PhotoApp allows us to generate images conditioned on camera viewpoints and scene illumination while using a pre-trained StyleGAN network as the rendering backbone. This shows us that converting the unconditional GAN into a conditional one is possible without any retraining of the generator. So what if we do not have access to such a supervised dataset for training? Jahanian et al. Use synthetic supervision for optimizing trajectories in the latent space which edit a particular property of the synthesis process. Generating synthetic data is possible for properties such as zooming and 2D translation, like the example here. However, this becomes very difficult for some 3D transformations such as editing scene illumination. Another class of methods does not rely on supervised pairs at all, either real or synthetic. A good example here is interface scan, which first uses an automatic annotation tool to annotate several properties of images randomly generated by a GAN. The method then computes a hyperplane which separates the latent vectors according to each semantic property. For example, one hyperplane could be separating the latent spaces based on gender. Moving along the normal of the hyperplane from any point in the latent space then leads to controllable synthesis. So this paper demonstrates this for multiple GAN architectures such as progressive growing of GANs and style GAN. While interface GAN finds linear directions, methods such as style flow can learn nonlinear directions for higher quality controllable synthesis using style GAN. Nonlinear manipulations can better disentangle the properties which should be edited from those which should not be edited. These methods, this one as well as the previous one, they need some annotation tool which might not cover all the scene parameters which you want to edit, and the annotated properties might not be directly related to the scene parameters we are familiar with in computer graphics. A tighter integration between GANs and classical graphics model is also possible, and there are some methods there which use inverse rendering techniques to guide the latent transformations. For example, we presented StyleRig at CVPR last year, where we used a 3D face reconstruction method to guide the latent transformation. Here we can reconstruct the 3D faces from images synthesized by StyleGAN using a differentiable face reconstruction network. And using this network, we can design our controllable synthesis module. We have a latent transformation network, RigNet, and the input to this network is a StyleGAN code vector and some target 3D control parameters. The output is the latent code which corresponds to the input edited based on the control parameters. The loss function uses the inverse graphics network and ensures that the edited property, such as pose, changes while everything else which should not be edited remains consistent with the input. So this architecture integrates a traditional inverse graphics pipeline with the StyleGAN latent space. After training, we can control the pose in any StyleGAN generated image. And you see the rendered mesh on the left and the result on the right. So the inverse graphics network does not need to be very accurate. It is not very complete, but the output, the controllability can still be recovered in the StyleGAN space. We can also change the expressions, so we can open and close the mouth. And we can also change the scene illumination. And just to reiterate here, the generator network of StyleGAN is completely fixed. We are only figuring out how to change the input latent vector, which leads to the desired editing in image space. Similar to StyleRig, the approach of Pan et al. Also uses an inverse graphics network to guide the editing function. In this case, the inverse graphics network is jointly trained along with the editing function, unlike StyleRig, where the inverse network was pre-trained. They show results on images of many different object categories using the StyleGAN network as the rendering backbone. So far, we have looked at some methods which use supervised pairs to expose 3D control in pre-trained GANs. We also looked at some methods which do not need fully supervised pairs, and they only need some annotations for random samples of the GAN. And finally, we saw that inverse graphics methods can be used to expose 3D control as well. And these methods require the least amount of supervision, and they are very often self-supervised. So all these methods can enable controllability just using transformations in the latent space of GANs. This implies that a GAN learns information about the different 3D scene properties, even though no 3D information was made available during its training. So the only training data GAN sees is a dataset of monocular images. Several papers have studied the properties of the latent space of several GANs. For example, GAN space shows that a simple PCA over latent vectors or intermediate features of GANs can lead to many interpretable directions. Higher quality editing can be obtained by restricting the edits to certain dimensions of the latent vectors. This shows that even if we do not have any supervisory signal, we can still find some meaningful manipulations in the latent space of GANs. While all the methods we have looked at so far keep the generator network fixed and only play with the latent space, there are some methods which do fine-tune the generator or even train it from scratch for higher quality controllable synthesis. There is a trade-off here. The methods which enable controllability on pre-trained and fixed models can usually be trained very fast, while training GANs from scratch is very expensive. The state-of-the-art models can take more than a month to train on a single GPU. For most real-world applications, controllable synthesis of random images generated by a GAN is not very useful. In most cases, we would like to edit real images captured by us. For example, we might want to edit portrait images of people we know. For this, we need to project this image onto the latent space of a GAN such that we can use any of the latent transformation techniques we have looked at so far. One way to do this is by designing an optimization problem. Image-to-style GAN is one such approach, and the method starts with an input image and an initial latent vector. A synthesis energy term is used in order to optimize for the ideal latent vector. The energy term consists of an L2 and a perceptual term between the reconstruction and the input image. Image-to-style GAN obtains very high quality projections of images onto the latent space of style GAN, and this paper shows that the latent space of style GAN is quite powerful. Even when the GAN is trained on portrait images, it is possible to find some latent vectors corresponding to images of cats or dogs or other object categories. While such a method can fit to an input image very well, the obtained latent vector might not be very suitable for editing using the methods we have looked at earlier. For example, the image-to-style GAN latent vector, when edited with StyleRig, often leads to results with artifacts. In our SIGGRAPH Asia paper last year, we resolved this by adding additional loss functions which also preserve the quality of editing of the optimized latent vector. Since we know what method we are going to use for the final editing operation, we can use it to provide additional information during optimization. In this case, we use the StyleRig network to obtain edited images. So once we have the edited image during optimization, we can add some face recognition terms which ensure that the identity of the person does not change while editing. So this gets rid of most of the artifacts we see in the edited images. Additionally, we add the energy terms used to train the editing method itself, which leads to even higher quality embedding. This method is designed for style GAN, and it also uses a course to find hierarchical optimization strategy in the latent space. So now with the updated optimization strategy, our method could obtain higher quality editing results of real portrait images. Abdel et al. And Wolf et al. Developed regularizers which are not specific to any one editing method like the previous approach. These regularizers are based on the analysis of the different intermediate spaces of the GAN. For example, it turns out that an intermediate feature layer of style GAN has Gaussian distributed output. This helps in designing simple regularizers which enable high quality projection as well as editing. For Big GAN, Hu et al. Developed a method which first transforms an input image such that it can be projected well onto the latent space of Big GAN. After transformation, an optimization problem is used to find the projection like in the previous case. The goal with the projection approaches is to obtain high-quality image reconstruction without moving too far from the distribution of latent vectors the GAN is trained with. Optimizing for image transformations such that it matches the training distribution better is definitely a good idea. So while these projection approaches we saw so far were optimization based, which means that we have to solve an optimization problem for every image we are given, there are also some learning-based methods in the literature. These methods learn a convolutional encoder which maps an input image to its latent representation. At test time, the projected latent vector can be computed very fast using a single forward pass of the encoder. So this is unlike optimization-based methods which can take up to a few minutes to compute the projection. Encoding and style used such an encoder for projecting portrait images onto the StyleGAN latent space and obtained high-quality reconstructions. The latent embeddings were shown to be useful for many editing tasks such as face frontalization. Restyle uses an encoder which iteratively defines an initial latent vector. So this is like a learned optimization method where the encoder is evaluated multiple times in order to reach the final latent vector. Such an approach leads to very high quality projections and offers a good trade-off between optimization and learning-based approaches. So we have seen that it is not only possible to expose 3D controls in pre-trained GANs, but it is also possible to edit real images using these methods. The latent representation of GANs are very useful, and we saw that it is possible to perform high quality synthesis even when a single image observation of the object is given to us. And while the state-of-the-art methods can obtain very high quality results, there are still many remaining challenges. For example, there are certain 3D parameters which cannot be easily controlled in pre-trained GANs. StyleGAN preprocesses images in a way which cancels out all the in-plane rotation. So the GAN also does not synthesize such images with in-plane rotation. This can be seen in this plot, which shows the distribution of different 3D parameters, and this one corresponds to in-plane rotation, which is always 0. Thus, control over this dimension is not easy with the methods we have looked at today. There also seems to be a trade-off between the quality of projection and editing. Many papers have observed that when the projection is smoother and we do not try to reconstruct all the high-frequency details in the input image, the quality of editing is better. When the quality of reconstruction is very good, like in the leftmost case here, the reconstruction is high quality, but the editing can be a bit unrealistic. As we move to the right, we get smoother reconstructions, but the quality of editing is better. While in this part of the course we only looked at 2D GANs, there are some methods which design the GAN in 3D. For example, in PyGAN, the output is a 3D volume which can then be rendered using volumetric integration for a realistic image output. These methods have some 3D controllability by design. For example, in this case, the viewpoint can be controlled explicitly. We will also cover such methods later in the course, so please stay tuned. And that's it from my side. Thanks a lot.
Hi, I'm Gordon Wettstein, and I'd like to tell you a little bit more about neural scene representations and rendering. Scene representations are something that most of us are working with on a daily basis, whether it's in robotics, graphics, physics simulation, autonomous driving, or 3D computer vision. All of these fields use their own handcrafted scene representations that are perfectly adjusted and engineered to serve any one of these purposes. But the thing is, handcrafted scene representations don't generalize well across these applications, and they're also limited in the way they can be trained or developed in the first place. So neural scene representations, which are basically learned representations that are differentiable, can really overcome some of these long-standing challenges in graphics and many other application areas. Neural scene representations allow us to learn data that include priors across scenes that we can use to solve inverse problems that are ill-posed. It allows us to represent multimodal properties of a scene, which can be important, for example, when not a human looks at them, but when a robot has to make a decision. And it can be useful for learning properties that are simply difficult to explicitly model. So there are many benefits of thinking about neural scene representations, and I hope I convince you of many of those in the rest of this talk. But one big question is, well, where does this representation actually come from? And in the context of AI, we typically then think about how to train them. And so, what is the data that we have that is widely available already today? Well, it is 2D images, whether they're computer generated or whether they're photographs of real scenes. We have an abundance of images online and in various databases. And so why don't we start with those, because they're already there? Well, then a very high-level general pipeline for a neural scene representation and rendering framework would be to somehow extract meaningful information from these images, distill those into a differentiable representation or a neural scene representation that typically uses abstract features with an inductive bias to be 3D also. And then we need a neural renderer on top of that that takes our scene representation and somehow renders it or projects it into the 2D images. So neural rendering techniques are basically just differentiable versions of sphere tracing, ray tracing, rasterization, or any other rendering technique that you may know, depending on what the representation is that is underlying them. So the output of the neural renderer would be 2D images again, and we can basically try to re-render the images that we gave as input to our neural scene representation and apply some kind of an image-based loss on those to train the system end-to-end. So this is what's called a self-supervised scene representation learning approach, because you don't need any manual input or annotations from a human to train this. You just need the images and send it through your pipeline and make sure that the pipeline outputs whatever you put in. And that's a very intuitive framework that way. Now, how do we think about a representation? What's a representation? Well, there are different types of representations, and we typically have seen a lot of explicit representations like voxel grids, point clouds, triangle meshes. These are what we're working with in graphics most of the time. And those are great, but they're not necessarily the best when you try to represent a scene. So over the last, I would say, few years, specifically in 2018, there were a couple of proposals in computer vision thinking about modeling 3D objects as neural networks, specifically coordinate networks or scene representation networks. So in this context, we have a neural network modeling the scene, or a visual scene, for example, that take as input a coordinate. So for example, the X and Y position of the 3D space. And they model quantities like the color, the semantics, the shape, or whatever else on the specific coordinate. So this is actually a continuous representation of a 3D scene that is parameterized by a fully connected neural network. And although the concept was introduced in the Deep SDF paper and also occupancy networks in 2018, our work in 2019 was the first to leverage such a continuous neural network parameterized representation using 2D supervision by including a neural rendering algorithm. So let me show you how this works. I mean, we're going to follow our general pipeline that we just saw, starting with multiple posed observations of a 3D scene, such as a car here. We're then going to model this scene representation network, which maps, again, 3D coordinate to quantity of interest, for example, a feature vector. And then we put a neural renderer on top of this. And in our context, we used a ray marcher that basically marches along the rays through the volume and accumulates the features in the volume. And that helps us render a 3D image by concatenating and aggregating those features. And we can then compare the rendered images to the observations with some loss function, for example, L2 or L1 loss. And we can thereby train both parameters of the representation and maybe any free parameters of the renderer, if there are any. Now, one thing that, this seems pretty simple, we can overfit this to one scene, but one idea behind this neural scene representation is that we can do more than traditional handcrafted representations by generalizing across classes of object. So for example, if we look at multiple different cars, then each of the cars is different, and we could fit a neural network separately to each of these cars. But there's probably some redundancy because all of these cars have common features like 4 wheels, mostly, a chassis, and a couple of other things. So what we can do, and what we did in our SRN paper in 2019, was to use this manifold assumption from machine learning, which basically states that, even though you need L parameters to parameterize every little object, if you have a class of objects, they can oftentimes be represented by a much lower dimensional subspace as basically lying on a k-dimensional manifold. And this can be enforced by modeling each of these objects using latent code vectors of size k, so these embeddings zi here, and each of the cars is then uniquely represented by these code vectors. Now the question is, how do you map the code vector to the actual car? Well, we used an idea that is known as hypernetworks. A hypernetwork is a neural network that predicts the parameters of another network. So this hypernetwork would take as input the code vector of a specific car and then output all the weights and bias values of the network representing any one specific car, or that specific car. Now, we can train this using multi-view images of many different cars. And in that context, we basically optimize code vectors for each of the target cars, for each of the training cars, and a single shared hypernetwork. So the entire class of objects is fully defined by a single network and these code vectors. So that's a very powerful idea, because the hypernetwork really learns a very strong prior that is generalizing across these cars. And the way we set up our scene representation networks makes it include an inductive bias that makes it inherently three-dimensional, because they take 3D coordinates as input and output some feature representation at that location. So using this idea and this generalization idea in particular is powerful, because now once trained on a specific class of objects, we can now take individual images of objects, so just a single 2D image, and predict the full 3D shape of these objects. And so you can see that most network architectures that existed up until then are basically simply not view consistent. They include a lot of artifacts because they don't have this strong 3D inductive bias, or they don't have the right neural rendering technique. But our combination of scene representation, network representation, and neural rendering allowed us to get pretty good results that extrapolate the single view into 3D, and they're pretty view consistent. So we did this for many different types of objects like cars and chairs. Here you can always see on the left the normal map, the synthesized view from a single input image, and then the ground truth video as well. So this works really well for these ShapeNet objects, and combined really neural scene representation, generalization ideas, and also rendering. So all of this was before NeRF. NeRF came along in 2020, early 2020, and I think one of the many big benefits and contributions of NeRF was that we were able to achieve this photorealism. So we were able to move from modeling these ShapeNet objects to modeling photorealistic scenes, and that's great. But NeRF is limited in overfitting to a single scene. There's no notion of generalization in there, which I just showed you. So that's kind of a slightly different tangent. And NeRF opened up a toolbox of different ideas that have been coming out and been published in computer graphics and computer vision since then. And one of the fundamental questions that our group has been focused on is to think about how to design the neural network architectures for these types of neural scene representations. And you can think about this in a broader context, let's say, by thinking about the types of signals they represent as something a little bit more generic. For example, these signals could be images, they could be 3D shapes, they could be 1D waveforms for audio, or other applications. And today we mainly built on discrete signal representations. For example, images are typically represented by 2D grids of pixels. 3D shapes are typically represented by 3D point clouds or vertices and meshes. Audio signals are represented by discrete 1D waveforms. And those tools work really well, but they have limitations. This idea of representing a signal using a neural network is powerful. And as I mentioned, this came up in 2018 was proposed by several groups simultaneously. And typically what people had been using were these multi-layer perceptrons that again take as input a 3D coordinate, for example, for 3D shape, and then output either whether that specific coordinate is inside the object or outside or on the surface, or it can also represent the distance to the closest point on the surface. That would be a signed or unsigned distance function. So it's just a fundamentally different representation. And again, one benefit is being able to generalize across objects, as I've already shown you. One limitation of these MLPs, though, is that they're not very expressive. Okay, so what that means is that traditional representation like meshes and voxels are limited in memory. You can only store so much in memory before you kind of run out of that. You don't have that problem necessarily, at least for these neural network-based representations, but the network has to be a reasonable size. And so then the whole representation is limited by the capacity of the network, because the capacity defines what the fidelity is and the level of detail that you can actually represent. And it just turns out that ReLU activation functions that most people are using simply don't have a very high capacity. So we've been exploring other ideas, and one simple idea was to use a periodic activation function in a network architecture that we called sinusoidal representation networks, or sirens. So this idea of a siren was introduced at NeRFs last year, and we demonstrated that very compact networks can represent very complicated signals really well. And these include 2D images, 3D shapes, 1D waveforms of audio, and also wave fields used for physical simulations. So let me try to convince you of this by showing you a first example. This is going to be an easy example where our input is a 2D domain in X and Y. We want to fit an image, but we don't show the network the image itself. We're showing it only the gradient of the image. So we're training the network representation on the gradient of the image. This is basically the Poisson equation. And again, here I'm comparing a couple of different nonlinear activation functions, and it turns out that these sirens that I mentioned are really great at fitting not only the gradient of the signal that it's supervised on, but also the image itself, the second derivative really well, really fast also, as you hopefully saw in these convergence plots here. This is just such a great tool. Being able to fit not only the signal, but also the gradients was really important for many applications in, computational geometry and beyond. In this context, for example, when fitting 3D shapes to point clouds, we want to place constraints on the surface normals, or maybe on the signed distance function, like the iconal constraint. They all involve mixtures of gradients of the representation and the representation itself. So it's actually really important for the representation to have well-behaved gradients. And as you can see here, our sirens can represent this complicated Thai statue really well with a lot of detail, whereas a comparable ReLU network is simply not able to capture that amount of detail, simply because it doesn't have the capacity. Here's a room size scene. Again, on the left, we see a ReLU network representing a 3D shape supervised on point clouds, and looks fine, but it's very limited in the amount of detail, whereas the siren representation you can see here actually results in fine detail across this relatively large scale scene. And this is a single global network representing the entire scene all at once. One aspect that I just want to briefly mention is that if you can model the signal and its gradient well, then this also works great for solving physics-based simulation problems. So for example, here we're solving the Helmholtz equation on a complex valued field that is constrained by the initial condition only, and immediately the siren fits these signals, whereas other representations like using ReLU or the hyperbolic tangent that people have actually worked on for a while in physics-based simulation just don't work very well. And so these sirens are really nice. And so far I've shown you that they can overfit to individual signals like images or 3D shapes, but I haven't shown you yet that they can actually generalize across scenes. Generalizing is an interesting topic for multiple different applications. And one of those applications are generative adversarial networks, so GANs. So one popular data set, for example, for GANs is CVPR. It's a collection of 2D images showing the headshots of celebrities, and 2D GANs then basically learn a prior across this space and are able to generate new faces. So we took on the challenge of trying to make that work in 3D using what architecture that we call PyGAN. It basically uses a siren backbone architecture to represent these 3D scenes. We train it only using 2D face images. And the thing is, we don't have multi-view supervision. It's only supervised on individual images of individual people. Our neural rendering technique is a neural volume rendering that is very similar to that of NeRF. You basically step along the ray and accumulate the features along those rays to project a 3D representation into a 2D image. What was really new was this backbone that's using sirens instead of the ReLU architectures. And then we came up with a new way to generalize across different objects using a mapping network that's pretty standard for GANs. but in particular, how we concatenate the mapping network into this backbone. And we used feature-wise linear transforms. So that's basically a multiplicative concatenation where we predict multiplicative weights that are acting on these nonlinear activation functions here. And that just works really well. I wouldn't say we're quite there to get photorealistic, high-quality results, but we certainly made a big step over some of the recent work that's inspired our work. For example, Hologan and Graph were the first works in that general space. But they're suffering from lots of artifacts that we were able to mitigate with our architecture quite a bit. Now, all of these techniques like NeRF, also PyGAN and others, built on neural volume rendering. And neural volume rendering is very slow. So that is a big problem. Neural volume rendering works by defining a camera, shooting rays through the scene, and then for every of these rays, you're calculating integrals where you sample across, basically along the ray to approximate the integral underneath. And it's simply slow because you have to take many samples. And for every sample, you have to evaluate if the full scene representation network. So a full forward pass through the network is required for every sample. And so we thought, well, wouldn't it be nice to come up with better integration schemes? From machine learning, we know that automatic differentiation is such a powerful tool that helps us train all of our neural networks and pretty much everything in AI. And it's all based on the chain rule for differentiation that we all learned in high school. Well, isn't there something equivalent for integration? And as seen by this little cartoon from XKCD, integration is actually a lot harder. There's not this one chain rule equivalent that you can use. It's actually very difficult to come up with like an automatic way of calculating these integrals. And for that reason, most people today in most applications use either Riemann sums, quadrature rules, or simply Monte Carlo sampling to approximate integrals. But again, for all of these applications, you have to query the network many times, and that's really the bottleneck. So we wanted to think about a better and maybe fundamentally faster way to evaluate these integrals. And our idea goes back to the fundamental theorem of calculus, which basically says that if you have an indefinite integral of a function psi, that's represented by the antiderivative phi, and then you can calculate definite integrals using the Newton-Leibniz formula by evaluating the antiderivatives at these 2 points of the boundary and just calculating the difference. So couldn't we just use that idea somehow to make it more efficient? And indeed, we can. And we came up with what I thought was a really clever idea that my team came up with. In particular, we use a multi-layer perceptron, like a representation network, for the integral network, for the antiderivative in this case. It turns out we can analytically calculate what the derivative of this network is. And the key here is that the parameters of these two networks are shared, but the architecture itself is different. So this grad network can now be trained to match whatever signal you want. Once it's trained, we can then rearrange its parameters into the integral network because they share the parameters. And we can now evaluate the antiderivative with just 2 function calls. So that's such a great idea. Well, the problem for neural rendering, for neural volume rendering, is that there's really several nested integrals. So it's turned out not to be quite as straightforward. We were able to speed up the rendering by factor of 8 or so, depending on some of the parameters that you set. But we did have to take a small hit in the quality of the rendering. But the idea of accelerating integration and developing neural network architectures for quickly computing integrals is really powerful and interesting. So I encourage you to look at that paper if you're interested in this topic. Another way of speeding up rendering times is to not work with volume representations and integration, but to actually work with surface representations. So in this case, we have a multi-layer perceptron that implicitly defines a surface. Its surface is nice because once it's optimized, you can actually extract it using marching cubes and just render it in real time using rasterization. And that's something that we explored in this neural LumiGraph rendering project that is being presented at CVPR this year. And not only do we achieve real-time frame rates, but even for a very small amount of cameras, like in this case, we only have 6 cameras or so, we can actually get pretty decent results with sharp features that can again be rendered in real time once it's optimized. So in summary, scene representation networks are really different from CNNs and RNNs and other network architectures. So it's an active area of research, and different network architectures make sense here. These representations need to be scalable, editable, fast to query, expressive. They have to have well-behaved gradients, and they have to be generalizable. So, you can't necessarily achieve all of these traits at once. But Neural rendering techniques like volume rendering and sphere tracing typically don't work in real time. A lot of work has been done recently on making it faster, though, and there's some really interesting work that came out earlier this year already on accelerating some of these data structures. These neural scene representations and rendering also have applications well beyond graphics and view synthesis, compression, learning priors, solving inverse problems, and many others. So this field is just starting out, and it's starting to spill over into robotics and many other areas where people are actively looking at this type of work. Just want to end by teasing some of our work that we're presenting here at SIGGRAPH this year on a new architecture that we called ACORN, an adaptive coordinate network that is as expressive as Siren or more, but that simply trains a lot faster on large-scale signals. So here we see a 16-megapixel image of Mars that's fitted to more than 30 dB in only 30 seconds. We can use the same framework to fit 3D point clouds really well. For example, this 3D object is fitted to a point cloud, and compared to other representation architectures, we get a lot more fidelity, and it's actually trained a lot faster too. So this is really exciting. And we're slowly seeing these network-based 3D representations being interesting for practical graphics applications because they're just getting to the quality and the runtime that we're hoping they would be. And so this is just a really exciting area. I hope you stay tuned with some of the other work in this course. And I'd like to thank my collaborators and students who have done all the hard work in this space, especially Vincent, Eric, Julian, David, Marco, Peter, Alex, Connor, and Jiarjun. So thanks for your attention, and thanks for attending the course.
Hi, my name is Vincent, and I'll introduce the section on novel view synthesis for objects and scenes. Let me first formalize the problem of novel view synthesis. The problem of novel view synthesis is concerned with, given a set of 2D image observations together with their camera parameters, we want to learn a model here in the center that allows us to take in these observations and then render the underlying 3D scene from arbitrary novel camera perspectives. And the framework that all of these models use is very similar. Let me walk you through a high-level diagram. So we are always given a set of image observations here on the left, and there will always be some kind of reconstruction algorithm that will go from the set of image observations to some representation of the underlying 3D scene. And now we want to render this scene representation, and for that we'll build a differentiable render. It has to be differentiable because we want to infer the parameters of this model in a deep learning framework. And this differentiable renderer will now take a set of camera parameters together with the scene representation and allow us to render the scene representation from arbitrary camera perspectives. And this is now what allows us to close the loop, because we can just simply render out the same observations that we have in our training set and supervise this whole model end to end using just a 2D reconstruction image loss. So the scene representation together with the differentiable renderer is what allows us to train this model just given a set of 2D image observations. Now, what if we only have a single image observation or very few image observations of the underlying 3D scene? In this case, the scene representation isn't actually perfectly constrained given the set of image observations. So what gives? In this case, we will have to build a prior-based reconstruction algorithm. So in this case, we will have to build a parameterized reconstruction algorithm that can learn a prior over the set of neural scene representations, and therefore allows us to complete information that is not contained in the context observations. Okay, so in the course of this little introduction, I will talk about a set of scene representations that are currently being researched and where current work has come out recently. And just one high-level note up front is that just in general, for all of these scene representations, both the scene representations and the renderers that they use are oftentimes inspired by classic algorithms from computer graphics. And this, I think, is just something to keep in mind. It's particularly interesting because we are basically leveraging these classic computer graphics algorithms, these classic computer graphics renderers and so on, to basically imbue our machine learning models with 3D structure that then allows us to generate null views with much less training data and with multi-view consistence and so on. Okay, first I want to briefly talk about voxel grid models. So the reason why I want to highlight this, I've just picked out 3 models. There's Deep Voxels, Neural Volumes, and HoloGAN, all from like 2 to 3 years ago, is that voxel grids were arguably the first 3D structured neural scene representation that people broadly used. And many of the ideas that are currently being researched are can already be found in starting in these papers. For instance, HoloGAN introduced the idea of learning a 3D GAN, a GAN for 3D structure, given only 2D image observations. Neural volumes used volumetric rendering together with voxel grids for the first time. So there's lots of interesting work in this area already. So why are voxel grids not the ideal candidate maybe for this task of null view synthesis? Because they are true 3D, so we can render out arbitrary 360 camera views from a voxel grid, and they are pretty high quality. One problem is that they do not allow us to learn these priors for few-shot reconstruction very well, just empirically. And the memory that voxel grids require scales cubically with the spatial resolution. And especially in computer graphics, we are concerned with high quality and high resolution. So this is usually not tractable for realistic large-scale scenes. So recently we have seen this rise of neural implicit representations. And the key idea here is that you represent a scene as a continuous function that maps a 3D coordinate to whatever is at that 3D coordinate. So it could be a color, it could be a feature, whatever. And we directly parameterize that function as a fully connected neural network. Now, here I've picked out 4 papers. On the left-hand side, there's scene representation networks and differentiable volumetric rendering. And both of these papers are concerned with this problem of few-shot reconstruction. So given only few observations of some 3D scene, can we reconstruct the 3D scene? Maybe even a single observation just. So this does work, but it only works for these kind of simple scenes, as you can see them here on the left-hand side. So on the right-hand side, you can see if we are willing to train a single model for a single scene, then we can achieve much higher quality and even photorealism, as you can see here with the NeRF, which has inspired lots of amazing follow-up work, and Ben will talk about this in a moment, and implicit differentiable rendering by Yarif et al. In NeRFs 2020. And maybe one thing to highlight here is that there's really 2 different ways of rendering neural implicit representations around right now. One is sphere tracing based approaches, which basically work by a shooting array and marching along the array to find the surface within the scene. And these are relatively fast. They require relatively few samples to find the surface of the underlying 3D scene, require fewer network evaluations, but the convergence with these methods is rather difficult, and they're a little bit harder to train as compared to volumetric approaches like what was popularized by NeRF, which have generally higher quality, are much easier to train, but are very, very expensive to render and require on the order of tens of seconds for a single high resolution image to render. And of course, since then, there have been a variety of cool extensions, such as the dynamic extensions to NeRF, which allow us to reconstruct non-rigid scenes, such as faces and so on. And Dan will talk about NeRFs in a moment, and that's going to be very exciting. Then, so to sum up implicit representations, the pros are that they are also true 3D. They can parameterize the full 360-degree scene. They are pretty high quality. They are compact, so no matter how many image observations we have, in the end, we end up with only the parameters of one neural network. And this admits us to learn a global prior, so a prior over the full scene representation. And this is what was exploited by these papers that I just highlighted. On the flip side, these methods are extremely expensive to render. And because at training time, we have to backpropagate through the renderer, this also means that they're extremely expensive to train. And this is a major downside. So there has been a recent line of work which tries to address this in a creative way, which I will refer to as hybrid implicit explicit representations. And the key idea here is that instead of parameterizing the whole scene as one large neural network, we have some data structure, such as a voxel grid, which coarsely represents the scene, and maybe in each voxel stores a feature. And then we have an implicit representation that is locally conditioned on the content of these voxels. And here I've picked out a few papers from this field. There's neural sparse voxel fields, and Lingjie will talk about this in a moment. And the key idea here is exactly that basically we have a voxel grid that stores features, and we locally condition a NeRF on these features. And she'll talk more about that. Then there has been a very exciting line of work, which instead of storing features in a voxel grid, basically takes the image observations and extracts convolutional features with a convolutional neural network from these images. and then conditions an implicit representation on features extracted from these images. And this allows some pretty cool generalization and single shot reconstruction. And it is orthogonal to these global priors that we had seen earlier, where previously we had learned a prior over the parameters of one implicit representation. And now instead we basically learn priors over patches, asking what does this patch look like from a different camera perspectives. And this is very exciting. It leads to very cool few shot reconstruction results. And lastly, I want to point out this paper that was recently published on unconstrained scene generation with locally conditioned radiance fields, where we parameterize a feature grid, a feature floor plan, and we locally condition a neural implicit representation on the features stored in this floor plan. And this enabled this generative model for 3D room scale scenes, which I thought was really cool. So maybe to sum hybrid implicit explicit methods up, these allow us significant speed ups over these implicit representations because we are not storing the whole scene in one large neural network anymore, but we now have basically discretized the scene again. And this does admit us the learning of local priors and things like few shot reconstruction. But on the flip side, we lose this cool property of implicit representations that they are compact, where we can store the whole scene in the weights of only a single neural network. Now we basically have discrete voxels and so on floating around again. And as a result, the priors that we learn are not global priors anymore. They're not scene-centric. So where in scene representation networks or differentiable volumetric rendering before, we might have learned a prior over cars. Now we learn a prior over patches of cars. Next, I want to briefly touch on multiplane images. The key idea of multiplane images is that we represent a scene as a set of planes, and at each plane we could store an RGB alpha value, and rendering then amounts to shooting a ray through these planes and smartly picking colors along each ray from these planes. And these multiplane images allow pretty high quality and fast null view synthesis. On the flip side, they are relatively large to store, and they only allow 2.5D null view synthesis. So they do not allow us to view something seen from the back. They only allow us to generate null views that are basically frontal parallel to the scene. Nevertheless, sometimes that might be all we want, and these multiplane images have seen some really cool progress recently and can lead to pretty cool results. Lastly, I also want to highlight image-based approaches because we have seen some pretty cool progress there recently as well. And there's, on the one hand side, stable view synthesis, which takes the set of images and then runs a multi-view stereo algorithm to reconstruct coarse geometry of the underlying 3D scene, and then uses this coarse geometry to reproject features extracted from a convolutional from the context images and render out null views in this way. And this works really well and gave fantastic null view synthesis results. However, it does require a multi-view stereo algorithm, but I think this is something to keep in the back, that this is a viable option, and for many approaches might be the right way to go for many problems. And then there's the recently published IBRNet, which I thought was also a very refreshing perspective on image-based rendering, whereby we pick rays from context images again, but without first reconstructing an approximate geometry of the scene. It's just a refreshing take on image-based rendering. And so to sum up image-based rendering, these approaches are also very high quality, can lead to photorealistic results. They are very fast as well. However, they do require us keeping the context images around again. So they are not a compact representation. They do not infer an object or scene-centric representation of the underlying 3D scene anymore. And so maybe to close this super brief overview, three directions of future work that I'm very excited about, which I think are three core problems that will need to be addressed going forward, is one, expensive rendering. So especially in these neural implicit representations, rendering requires hundreds of samples to render a single camera ray. And this is, as I had mentioned, both at training and at test time, which makes these methods extremely expensive to train and makes rendering take forever. So there are approaches to speed up the rendering in NeRF, for instance, but these usually only speed up the rendering at test time and not at training time. And so I think this will be a very important direction for future work. And this, of course, also applies to things like let's say we want to do non-Lambertian scenes, we want to do null view synthesis for reflections. And right now, it's kind of inconceivable that we could do multi-bounds ray tracing if every ray costs us hundreds of evaluations of some underlying neural scene representation. So addressing the cost of rendering will be a key factor going forward. The second point is generalization. So we have seen these local conditioning methods, which allowed us much stronger out of distribution generalization recently, which has been really cool. On the flip side, this doesn't learn an object-centric representation, which might be useful for computer vision or robotics applications that are downstream. And also, this doesn't learn a space of scene representations. So there is, for instance, not a latent code that represents the whole 3D scene. So there is an open question here if maybe we can have the best of both worlds. Can we maybe learn compact representations of 3D scenes, while at the same time exploiting these benefits of convolutional neural networks, such as shift equivariance, that allow local conditioning methods to generalize better than global conditioning methods? And lastly, there's the problem of scene understanding. So of course, many of these solutions are addressing computer graphics problems, but fundamentally the problem that we're solving here is a representation learning problem. We're learning some representation of the underlying 3D scene. And these representations are useful across many different domains. And I think it will be really exciting seeing applications of these neural scene representations in robotics or in computer vision applications going forward. And with this, I'm really looking forward to Ben's and Dan's and Lingjia's talks on NeRF, on neural sparse voxel fields, and on NeRFs. And this concludes this short introduction, and thanks for your attention.
Hi, I'm Ben Mildenhall, and I'm going to give an introduction to neural volumetric rendering, particularly in the context of neural radiance fields and other related work. Okay, let's unpack this phrase a little bit. So as we've seen already in this course, neural rendering is a really broad umbrella of techniques, but I'm going to scope out a particular set of methods here. So by rendering, I'm referring to the typical 3D computer graphics problem of determining what the incoming radiance or color value is for some ray that travels through 3D space, and then building up rendered images as collections of camera rays, just like in conventional ray tracing or path tracing. And I'm just noting this to differentiate it from 2D neural rendering techniques like GANs or other CNN-based methods. And volumetric here, it means we're not doing hard ray surface intersections. Because we're thinking in the context of machine learning, soft continuous functions like volume rendering are much more easy to differentiate and optimize through. There has been a lot of excellent recent work done on differentiable path tracing and differentiable rasterizers using triangle meshes, but our goal is to build renderers that actually work natively in standard autodiff frameworks like TensorFlow or PyTorch, without the need for any custom low-level code. So the simplicity and effectiveness of volume rendering kind of wins out here. And finally, neural means something a little unconventional in this case. Rather than having a network that's going to take in whole images and spit out other images or some scene representation, we're going to use a network directly as a function that represents the spatial properties of a scene. So you might put in a 3D XYZ location and then get out a color, a volume density, a BRDF parameter, or some other attribute of the scene. And the motivating task here that I really like to work on and think about is novel view synthesis. So I want to go out and take 20, 30 pictures of a flower like this, put them through some method, and then be able to render novel, high-quality views of the same scene from different viewpoints. Okay, here's an overview of how I'm going to build up this problem. So first, I'll talk about the volumetric rendering mass we need to understand NeRF. Then I'll talk about how you can use neural networks as a representation for spatial data signals like images, videos, or volumes. Then I'll show how those are combined into neural radiance fields. And finally, I'll quickly skim over a couple of improvements and extensions that people have made to NeRF. Okay, so let's get into this volume rendering math. A lot of you at SIGGRAPH probably are familiar with the history of volume rendering methods. There's this book, Radiative Transfer, that's very, very highly cited, and people kind of lifted a lot of the physical definitions of volume rendering quantities from this, particularly the meanings of absorption, emission, and different types of scattering. And these sort of techniques were quickly adapted for other purposes besides physically based rendering, like visualizing medical data volumes. And this is also very closely connected to alpha compositing, which was developed in a similar time. Now, most modern path tracers have sophisticated Monte Carlo methods implemented to allow them to render volumetric effects in movies and games, like smoke, fire, fog, and clouds. People have also been using volume rendering-like methods in machine learning for a couple of years now, starting with methods like this 3D shape reconstruction paper from Tulsiani et al. That has a probabilistic sort of rendering method for converting 3D voxel grids into 2D images that's very similar to alpha compositing. And if you scale up similar methods to these to really high resolution RGB alpha voxel grids, you can get really nice results out of machine learning methods that convert from input images into those voxel grids. Okay, so that's a little context. Now I'm going to discuss the derivations of the volume render equations that we use in the NeRF paper. I really want to talk about this because it's not totally self-contained within the text, but there's some pretty nice intuition behind it that I think a lot of machine learning people can appreciate. And I'm going to put a citation down here for this Max and Chen paper. It's not actually cited in NeRF originally, but it's a really nice, clear, and understandable description of this rendering setting. Okay, so in NeRF, we assume we have this cloud of tiny, infinitesimally small colored particles. This is not totally physical. There's not going to be any kind of scattering or multiple bounces within the volume. If you have a ray that's traversing through the scene, it's going to go through the volume until it first hits a particle at some distance t along its extent. Then we're going to return the color from the cloud at that location back to the camera. But this is actually more of a fuzzy soft event in practice. We assume that we have a known function sigma that tells us how likely a ray is to hit a particle at each point in space. And this is referred to as the volume density. But this density only tells us independently at each point along the ray if it's going to hit a particle. We want to find the expected first hit, so we need to know how likely it is that a ray doesn't hit anything else earlier along its extent. And this probability is called transmittance. And we assume that the way we characterize the volume is just by its density, and that we're going to have to calculate transmittance from that ourselves. And these two functions are related by this probabilistic fact. The event that a ray doesn't hit something within two different intervals are independent, so their probability can multiply together. So we can basically take the probability a ray doesn't hit something in this huge extent before t, and the probability it doesn't hit anything right at t, and combine them together. And then if we swap in our original equations here, we get this nice differential equation that we can solve directly for t. If you split up this differential, you get this in terms of t and its derivative. And then you can rearrange and recognize the derivative of log transmittance on the left here. So the simple solution is just to integrate and get this expression for transmittance in terms of density. So now we know the exact formula for transmittance. We can combine these two events together. Probability you hit something for the first time is equal to the probability that there's no previous hits times the probability that you now hit something at t. And this gives us this exact expression for probability you stop at t along the whole ray. And if you integrate this against color, you'll get the expected return color value, which is exactly what we need to figure out the color of a camera pixel. But this is a bit of a nasty integral since there's this hiding integral inside the exponent inside this outer integral. So we can really only approximate this integral, not directly evaluate it for any kind of complicated color in sigma. We're going to use quadrature to break it up into n different segments, and which do not need to have a fixed step size between them. And we'll assume that color and density are close to constant in each of these intervals. This means we can break up this larger outer integral into a sum of smaller, now analytically tractable inner integrals. But there's one catch here. Even though our density and color are piecewise constant, transmittance is not piecewise constant. And it's important to deal with this because if you have a very high density or a very long interval, the earlier part of that segment will occlude the later part. Okay, so let's take a look at this transmittance term and see how we can evaluate it. We can break up transmittance into the accumulated transmittance from all previous segments along with the partial segment we're currently traversing. So all the previous segments can just be analytically added together along with their lengths to produce this TI transmittance value. And then partway through the current interval, we can just evaluate this partial integral here to get this exponential decay function that varies with density and distance you've traversed. So going back to our quadrature expression, we can sub these in and factor out the constant terms. And now we have a very easy integral to evaluate. So we do that, and then we can cancel out this sigma I term that's sitting inside each of the added up quadrature estimates. And this is good because it means our estimate is now going to be bounded. That 1 minus exponential term is always between 0 and 1, and we can't have estimates that really go crazy if sigma is very high. We can also take a look at this particular 1 minus exponential expression and rewrite that as alpha I, a traditional sort of opacity value. And if you substitute that back into the equations we just derived, you can see it actually directly corresponds to the normal alpha compositing over operator, which really connects us to all the previous work on view synthesis via volume rendering. If we put this all together on one page, this is how we would estimate the color of a ray traversing through the volume parameterized by this color and volume density. So our next question is going to be, what are color and sigma at each point in space? How are we going to store these values and retrieve them when we're doing volume rendering? And this leads into the next topic. How can we use neural networks as a way of storing spatial data like this volume density function really compactly and efficiently? So when we're dealing with volumes, it's a very complicated 3D function. So just for the sake of simplicity, we'll drop down into a lower dimensional toy setting with 2D color images. Obviously, we usually store images as simple 2D arrays. To grab the color of a pixel, you just have to index into this 2D array and take the RGB color template that's right there in memory. But what if we trained a neural network to learn this pixel to color mapping instead? We can take that 2D pixel coordinate xy as a pair of floating point numbers, put it through this network, and then ask it to give us back the RGB color of the corresponding pixel. This is a really simple supervised learning problem, and we can just use gradient descent to directly train the network weights and see what happens. And of course, you could do this with any spatial signal. Just put the coordinates in and get the signal value out on the other side. So if we take a look at what happens if you directly train a network like this, it actually fails to represent any of the high frequency content in the image. And this is really a characteristic problem of standard MLPs or fully connected networks. They just cannot represent these low dimensional high frequency functions directly. However, we found that there's a really convenient and easy solution. You just have to pass those low dimensional input coordinates through a high dimensional high frequency mapping before sending them into the network. If you do this, you can now see that the network really quickly converges to learn all of the high frequency content in the image. Okay, so what does this input coordinate mapping actually look like? It's really easy. You just get a tall skinny matrix B that's going to map your coordinate vector x of those 2D or 3D coordinates up into a higher dimension, and then you pass those high dimensional vectors through sine and cosine. And this is exactly converting your linear coordinates x into a list of Fourier basis functions, basically. This is the same effect you're getting from positional encoding, what we called Fourier features in our work, and the first layer of a siren network as well. Here's a simple example of what this looks like in 1D. On the left, we have a basic spatial coordinate, and on the right, we see what happens if we pass it through a positional encoding that maps it to exponentially increasing in frequency sinusoids. And the same thing in 2D. So if we take a ramp in x and a ramp in y, just basic pixel coordinates, we can pass them through a series of random Fourier basis elements, which will have a random orientation and randomly changing frequencies as well. It turns out that the frequencies present in the B matrix can really influence the training of the neural network. So here, first we're showing the image that's learned inside a neural network, as we were explaining before, and then its performance versus the frequencies present in B, both in terms of training loss, like how well it memorizes the pixels we supervise, and test loss, how well it interpolates continuously between those pixels. And finally, we're showing something that's basically like the network's interpolation kernel. So when it's wide, it'll be over smooth, and when it's too narrow, it'll be over fit. And this is explained more in our Fourier features paper cited below. Okay, so here we're starting off on the left-hand side of the plot, where the frequencies are too low and the network is not able to represent any of the high-resolution detail in the image. If we go all the way over to the right with a really high-frequency B matrix, we see that the learned image exhibits aliasing. It's not interpolating well between the pixels we supervised. And of course, the optimal set of frequencies for the B matrix lies somewhere between those two extremes. Basically, we want to max out this test loss without going too far and making too much high-frequency content available to the network. Okay, so that's how you represent a signal inside a neural network. And this leads directly into NeRF. NeRF is the combination of these two concepts that I've already explained. We use a coordinate-based network to represent color and volume density across space, and then we apply the volumetric rendering model I described before to make pictures. Previous machine learning-based view synthesis work usually explicitly stores RGB alpha volumes as voxel grids, but here we're just replacing that with a network, which ends up substantially compressing that data. And it also means we can throw in another couple input coordinates for free. So we're adding this ray direction as well to let the color of particles in the volume vary when they're viewed from different angles, just like shiny objects would in the real world. In order to recover this NeRF volume, we just use gradient descent applied to a rendering loss. So we pick some input image we have of a scene, we render the NeRF volume from that camera pose, and then we just compare it to the ground truth image. And over many gradient descent steps, this encourages the colors and volume density to converge to reproduce both the training images and generalize to any novel view of the scene. Here's a couple example results from real-world scenes. So I just took these with 20, 30, 40 images from my cell phone, and then I ran this through CalMap to get poses, and then I trained NeRFs for each of them. We're able to get back a lot of fine geometric detail and some amount of realistic view-dependent effects for these scenes. And each of these is just encoded in 5 megabytes of neural network weights as well, which is a really astounding level of compression for scenes this complex. We're also able to do these hemispherical captures of synthetic scenes, which have a really, really high level of parallax. There's only 100 input images used to recreate each of these, which might sound like a lot, but in terms of view synthesis, it's pretty undersampled. So one detail I just alluded to before was that we're passing ray direction into the NeRF network, not just 3D position. And this does mean it's able to represent view-dependent effects like those shiny objects. And if we take a look at what the neural network learns by probing it at a fixed XYZ location but manipulating the viewing direction input, we can see exactly what kind of specularities it's thinking about. So here's a visualization of that for 2 different points on this ship scene. We have one on the side of the ship and one in the water. And you can see at this extreme grazing angle, both of these points have quite a bright white specularity that appears. And looking at these 2 circles, this is actually looking at a hemisphere of outputs from NeRF as you query it continuously in any output viewing direction. And you can see it's kind of put this blob where that output specularity appears. And we also visualize this in some of our real scenes. So this is kind of a transpose of the data I showed before. Instead of showing it over space, showing it over time. And it kind of pulls out the specularity that NeRF has learned on the side of the stove. We can also just throw out the color data entirely and visualize the expected termination depth of a ray through the density field. And that basically gives us a depth map, and we can see how good the geometry NeRF has learned from these input views is. Okay, so that's a quick overview of the basic premise of NeRF. So now let's see what's wrong with it. This is a really whirlwind tour of some of the ways people have improved on NeRF recently. And this is not just stuff I was involved in. There's a staggering amount of great work from a lot of different research groups happening right now. One recent project I was on was this MIP NeRF paper that addresses the fact that these coordinate-based networks so far are just point sampled, which means that the renderings we get out of them are not correctly anti-aliased. We found that if you actually pre-filter your positional encoding mapping, you can get the network to learn a representation with a continuous level of detail, which means you can render it up close and far away and still have it be correctly anti-aliased. There's been a ton of recent papers on speeding up the NeRF rendering process. Our brute force volume rendering approach in the original paper takes about 30 seconds per frame, and I think actually all of these papers can do 30 frames per second. So most of them go back in the direction of using voxel grids to represent the scene in some way, trading off some of the memory efficiency of NeRF for better speed. As well as rendering, the NeRF training process is really slow, and it can't generalize across different scenes. So people worked on that problem to basically make feed-forward kind of equivalents that directly map from the input images to a volume density and color field. And this can basically achieve the same quality as NeRF with just a couple minutes of fine-tuning on a new scene instead of hours or days. And one of the other main flaws of the basic NeRF formulation is that it really needs a static scene with one fixed lighting condition. And there have been a lot of dynamic NeRF papers to address this, as well as other methods that make it more robust to, or even capture the appearance variation under different lighting conditions. That's just a really quick summary. Check out this nice GitHub repo for many more examples of follow-ups. And thanks for listening to my talk. I hope you enjoy the rest of the course.
Hi, I'm Lingjie Liu from Max Planck Institute for Informatics. Today, I will talk about how to accelerate the rendering process of neural radiance field at inference time. First, I will review recent works on neural scene representations, especially the state-of-the-art approach neural radiance fields. In computer graphics, achieving photorealistic free viewpoint rendering is challenging because it's difficult to acquire a detailed appearance and geometry model. Recently, neural scene representations and the neural rendering approaches have been proposed to address the limitations of classical rendering methods. This method learns scene representations to encode both geometry and appearance from only RGB images for novel view synthesis. Neural scene representations and neural rendering have a wide range of applications, such as creating photorealistic avatars for VR and AR, relighting, dynamic scene rendering, and free viewpoint rendering. Neural scene representations and the neural rendering approaches can be categorized based on the type of scene representations. Here, neural radiance field, also called NeRF, has attracted a lot of attention recently, since it can synthesize a very high quality result from novel views. With NeRF, the entire scene is represented as an implicit function encoded by MLPs. This implicit function maps a point P on the ray along with the ray direction V to the color and the volume density at P. To synthesize an image, NeRF densely sampled points on each camera ray and accumulates the colors and the densities of the sampled point on the ray to get the color at the corresponding pixel. NeRF can synthesize photorealistic images if there are sufficient samples along the camera ray. However, NeRF suffers from a slow rendering process since a large number of the sample points need to be evaluated using the MLPs. For example, to render an image at 2K by 1K pixels, with the default setting of NeRF, 192 points are sampled along each camera ray. Then we need to call the MLPs for about 400 million times in total. If we used the NVIDIA V100 GPU to render this image, it would take 100 seconds. So how to accelerate the rendering process of NeRF? There are two possible ideas. First, the number of the sampling point along the ray may be reduced. Second, we may reduce the runtime for each pass through MLPs. For example, we can use a shallow MLP. We first introduced our work, Neural Sparse Voxel Field, which is based on the first idea. This work was presented at the Neural EVES last year. Our main insight is to avoid sampling point in empty space as much as possible. To this end, we proposed a hybrid segmentation, neural sparse voxel field, or NSVF for short. NSVF defines a set of voxel-bounded implicit fields organized in a sparse voxel octree structure to model local properties in each cell. With NSVF, rendering novel views can be accelerated by skipping empty voxels. Typically, our method is over 10 times faster than NeRF in the rendering process. Our method learns NSVF from coarse to fine from a set of post 2D images of the 3D scene. Next, we will describe the details of NSVF. Unlike a previous approach that modeled the entire scene with a single implicit function, NSVF models the scene as a set of voxel-bounded implicit functions. Here we assume that the non-empty part of a scene are contained in a set of sparse bounding voxels. We now describe the building block of NSVF, a voxel-bounded implicit function. For a given point P inside voxel Vi, this function f theta I takes a voxel embedding and the camera ray direction V as input, and output the color and density at P. The voxel embedding is defined as follows. Here, the GI tilde are the learnable feature vectors stored at 8 voxel vertices. Compared to using only the 3D coordinates of the point P as input to the function, as done in NeRF, our voxel embedding encodes more region-specific information. This local nature of this voxel embedding simplifies the learning of scene reputations as well, therefore facilitating high-quality rendering. Next, rendering NSVF is performed in 2 steps: ray voxel intersection and ray matching inside voxels. This process is very efficient since we can avoid sampling point in empty space. To compute ray voxel intersection, we applied the AABB intersection test for each ray to efficiently check whether a ray intersects a voxel or not. This test can readily process millions of voxels in real time. After getting all the intersected voxels, we uniformly sample point along the ray inside each intersected voxel for color accumulation for the ray. Here we compare our sampling method with the sampling method in NeRF. To focus the sampling on more important regions, NeRF learns 2 networks, where the second network is trained with the samples from the distribution estimated by the first network. However, this further increases the training and inference complexity. In contrast, NSVF does not employ a secondary sampling stage while achieving better visual quality by skipping the sampling in empty space with the sparse voxels. To speed up the rendering process, we apply early termination for solid objects. This is based on the observation that for solid surfaces, the volume rendering method dispersed the surface color along the ray. We therefore used a heuristic to stop evaluating point earlier based on the accumulated densities. Since the rendering process is fully differentiable, NSVF is trained end-to-end through backpropagation by comparing the rendered images against the ground truth input images without any 3D supervision. The sparse structure also allows us to use a progressive strategy to train NSVF. As shown in this figure, NSVF is trained from coarse to fine. Starting from the initial voxels, the sparse voxels becomes more and more accurate and converge to the ground truth geometry as the training progresses. We will provide more details. We start by learning implicit function for an initial set of coarse voxels enclosing the entire scene. To further improve rendering efficiency, we proposed a self-pruning strategy to efficiently remove empty voxels during training. We predict whether a voxel is empty or not by checking the maximum predicted density from the sampled point inside the voxel. Since this process does not rely on any additional modules or inputs, it's called self-pruning. After certain steps of training, we have the size of voxels and the size of array matching steps for next stage. When having the voxel size, we split each voxel into 8 sub-voxels and assign new feature embeddings at the vertex of the sub-voxels. This essentially increased the model capacity progressively in order to learn more details of the scene during training. Here we show the quantitative comparison with NeRF and another 2 methods, SRN and neural volumes on 4 datasets. For rendering quality, NSVF outperforms all the baselines on almost all datasets. Note that NSVF with early termination with the parameter epsilon is 0.01 produces almost the same quality as NSVF without early termination. Here we show the rendering speed comparison. Here the x-axis represents the foreground to background ratio, and the y-axis is average rendering time. The blue curve is NeRFs without, and the green and the red curve represent NSVF without and with early termination respectively. It's clear to see that NSVF achieves a very low latency similar to SRN and the neural volumes, and much better than NeRF. And with the early termination, the rendering process can be further accelerated. Here we show the visual comparison of our method NSVF with NeRF on several things. So here we can see NSVF can recover more fine level details. For example, this scene structure is better. Also, NSVF is 10 times faster in rendering than NeRF. Here we show another example. This example is from the wheel tanks and temples dataset, and we can also see that NSVF can capture more details. NSVF supports zoom in and zoom out effects. Here we show the result of using NSVF to render a dynamic scene. We can also interactively control the camera pose and synthesize novel views for large-scale indoor scenes. By interactively editing the sparse voxels, we can edit and compose more complex scenes. Although our method is typically 10 times faster than NeRF, it is still far from real-time performance. That is, rendering with NSVF is about 1.1 FPS, while the real-time rendering requires over about 25 FPS. Therefore, further research on acceleration is needed. Now I will discuss some recent strategies for accelerating NeRF rendering towards real-time performance. In fact, Some of this method already achieved real-time NeRF rendering. The first strategy is to make full use of the sparse voxel octree structure to store the pre-computed network output on each voxel leaf at inference time. The insight behind this is use caching to trade memory for computational efficiency. There are 3 recent works applying this strategy to real-time NeRF rendering. More specifically, what they do is they first train a NeRF-like network to map the point position and the camera view direction to the density and the color at that point. After training, they extract the non-empty voxels and build a sparse voxel octree from the learned scene representation depending on the predicted density. Next, they pre-compute the color and the density for each voxel and store in the sparse voxel octree. To render image for each sample point, they copy the color and the density either from the nearest voxel vertex of the sample point, or calculate the color and the density while trilinear interpolation of the 8 vertex of the voxel it belongs to. So this strategy bears considerably similarity to NSVF. However, directly using the NeRF model for this caching operation is not feasible because of high data size. Therefore, this method proposed to split the NeRF network into a post-dependent network and a view-dependent network. Here I give an example. A similar idea is also used in Next. Please refer to the original papers for details. The second strategy for acceleration is to decompose the entire scene into many small parts and use a shallow network to encode each part. A representative work is a KiloNeRF. They use the thousands of small MLPs to collectively model the scene content in thousands of sparse voxels for rendering acceleration. A similar strategy was used in DERF, which decomposed the scene while Voronoi spatial decomposition and used a small MLP for each part. The third strategy is to apply more efficient sampling with the depth guidance. DuNeRF accelerates the rendering process by first predicting depth for each camera ray and then sampling only in the neighborhood of that depth. However, this method requires the depth supervision for training. Another speed-up strategy is to learn color integration with a neural network as proposed in AutoInt. Here is a list of all the works I have discussed in this talk. That's all. Thank you.
Hi, my name is Dan Goldman, and I'm happy to present here as part of this course on advances in neural rendering. And I'm going to be talking about towards instant 3D capture with gelato and NeRFs. And I've asked a former intern of ours at Google, Kunhan Park, to help present this. He's not in the program, but I wanted to acknowledge his participation, and he'll be giving the second part of this talk. So what do I mean by towards instant 3D capture? When most of us who have been in computer graphics and computer vision for a while think of 3D capture, we think of expensive cameras and big rooms. And we'd like to change that. We'd like to see moving towards more consumer equipment and capture environments that you can have anywhere you like. So today we're going to be talking about 2 recent papers from our group at Google Research. The first one is called Gelato, and this enables high-quality real-time rendering within a category of objects. And the key point that I want you to come away with is that we can do few-shot reconstruction with these pre-trained category models. So you just need a few images of a novel object that you haven't seen before in order to do really high quality appearance reconstruction. And the second paper is called NeRFs, and the goal of this one is casual capture with a handheld cell phone camera. And in this paper, we're going to be modeling the geometry and appearance of deforming objects, and we call it NeRFs because, of course, killer app for this is being able to capture 3D selfies. So I'm going to start by talking about Gelato. And this is work that we presented at ECCV in 2020 with a number of colleagues from Google Research. Sofiane Bouaziz is now at Facebook. So what's the topic here? The topic is we want to do neural rendering of object categories. And so this might be cars, it might be chairs. And there have been a number of attempts at category level modeling of objects for neural rendering. Scene representation networks is one that's shown here. And for the most part, they get moderate image quality. I mean, you can certainly recognize what the object is, but they don't necessarily have the high fidelity of the original images. And importantly, they don't really improve the more views you give them. It's the additional supervision that you get from other viewpoints doesn't actually improve the reconstruction after, in this case, 50 views. You still have a relatively blurry representation of the chair and the ambulance on the upper left there. And this is work from Vincent Sitzman, who's presenting in another part of this session. So our objective here is to model an entire object category, and we'd like to take advantage of prior knowledge in order to do high quality reconstruction. So we're willing to spend some compute time building up this prior so that we can do very few shot reconstruction later on. And we'd also like to have a representation that we can render in real time. So an observation that we made is that neural textures, this is work from Justus Tias et al., who's also presenting in this session, that these are somewhat robust to coarse geometry. And I'll talk a little bit about what this model is, but the image on the right is taken from the paper, Deferred Neural Rendering, and shows that even as your geometry proxy gets more and more coarse, you still have pretty high quality appearance reconstruction. And so we thought this was interesting for representing object categories because it meant that you didn't necessarily have to have geometry that matched every object in the category. It could be approximate geometry. So we thought, what if we could represent some relatively complex geometry? We're going to use the example of glasses here with just 3 quads with neural textures attached. So these are not traditional textures. These are high-dimensional textures where we don't really know exactly what the features mean, but they encode something about the view-dependent appearance of these objects. And you can think of this as sort of a neural version of clouds of billboards. So billboards have been used in games for a long time as very, very low geometry representations of fairly complex objects. And you can make things that have a lot of geometric or at least visual complexity out of a small number of these clouds of billboards. So the deferred neural rendering model is you have some geometry that's given, that's sort of, we figure out what the pose of that geometry is outside the scope of the neural machine learning part. And we're going to learn a neural texture that is applied to each of those polygons that's in the proxy. We're going to sample it according to the pose, and then we're going to run that sampled texture through a neural renderer, which is also trained. And we're going to train that so that the images that come out of it have the appearance of input images. So for our case, again, looking at glasses, that neural texture needs to encode a number of different things. It needs to encode wherever the geometry differs from the proxy's geometry. It needs to encode the view-dependent effects, such as specular highlights, and also, in this case, occlusion between proxies. So we're not representing the holes in the glasses. We're not really representing the complex visibility representation, the visibility relationships between the glasses and, for example, the temples. And so the neural texture needs to actually encode something about that. So we chose eyewear as a test case because they're small, so it's easy to capture in a lab. There's lots of intra-category variation. Every pair of glasses looks pretty subtly different from every other. And they have some interesting view dependence. Many of them are shiny or colorful, and so they look different under different viewpoints. So to train our prior, again, I said we were willing to spend some time in the lab to build up a prior of what glasses look like. We captured a data set of 576 poses of 85 eyeglasses. We built this eyeglasses robot in order to capture these. And we actually have 4 conditions per pose. So we're able to light up that hollow head so that we can do some Laplacian matting to extract some clean mats. And it's actually a combination of difference matting and Laplacian matting, which is described in more detail in the paper. So out of this, we get a computed RGB and an alpha mask. And the alpha masks aren't perfect. You can see there's some remnants of shadows. We're still able to train with it, but you will see some remnants of those shadows in the reconstructions that we get as well. We also compute a rough voxelized shape using voxel carving. We're not really going to use that shape for any part of the reconstruction, but we are going to use it to figure out an optimal pose for each of our 3 proxies. These are the polygons on the sides and the front. So neural proxies, in this case, are going to allow us to have a category level model. So we augment the model of deferred neural rendering with this latent space, and that's the Z on the left. And that's actually going to, there's a network that's not shown here, which is going to determine what our neural texture is, depending on that latent Z. And in a little bit more detail here, that latent code Z is going to feed into an MLP, which gives us a higher dimensional code W, and that's actually going to be the input to generators for our neural textures. Again, all the details can be found in the paper. I'm just going to give you an overview here. Those neural textures are resampled according to the pose of those polygons and the viewpoint of the camera. And then those deep textures, so this is the sampled proxies image on the left here. You know, this is actually a high dimensional representation. It's not just an RGB representation. And then we have depths and normals, and all of that gets fed into a UNet. And the output of the UNet, unlike deferred neural rendering, which gives us only an RGB, we're actually going to ask it to give us both an RGB and an alpha, and we use an L1 loss for robustness. And then we're going to train against a composite, and we have both L1 and VGG losses against that composite. So here are some of the interpolations that we can do. So we can actually take that Z code and we can slide it between one pair of glasses and another to smoothly interpolate from one style of glasses to another. And you'll notice that even throughout this interpolation, the glasses stay relatively whole. And of course, we can also do pose variation while we do those interpolations. So this is a little bit crazy on the bottom, which is why I fade into it. So you can see the glasses are both changing style and pose as we go through this animation. Now, there are some cases, such as on the lower right, where the genus actually changes. So there's actually a whole, there's 2 different bridge elements, and those get fused into one. So in those cases, we don't have sort of a continuous, smooth transition from one pair of glasses to the other, but in most cases we do. So where I think this method really shines is that we can do this few-shot reconstruction. This is a pair of glasses that we did not use in training, but we can still regress a latent code for its Z. We can regress a transformed latent code W. And then we can optimize the neural textures and fine-tune the network parameters to match those 3 input views. And you'll see we get a very high-quality reconstruction out of it. Here's another example, and I want you to notice there's actually specular highlights that appear, in particular on the bridge. You can't really see those specular highlights in these input images, but the model knows that other glasses in similar situations have specular highlights and is able to reconstruct something plausible there. Here's another example with more specularities on the bridge. But what I want to point out is that the real strength here is that we only need a few images to do this fine-tuning of the category level model. And in fact, we get similar quality fine-tuning with the fine-tuned category model at only 10 images, where optimizing from scratch, you need 30 images. And likewise, there's a pretty big improvement here. Even with 30 views doing the fine-tuned category model, you get better performance than the version that's optimized from scratch. So this method does have some limitations. This few-shot reconstruction does assume that we know the ground truth pose and we have some proxy geometry that matches it. So an interesting area of future work will be to train with pose and geometry estimation in the loop. Another point is that we've baked the lighting into the model. So we're definitely interested in trying to build in, so we're interested in actually capturing some objects in a light stage where we can actually vary not only the camera view but also the illumination. And then include lighting in our latent code representation so that we can have a separate latent code that represents the illumination condition. So in summary, I want you to take away these little tidbits. Gelato is an appearance representation for modeling object categories. Neural textures can accurately reproduce the appearance of even very thin structures and reflective materials that would otherwise be hard to capture using traditional 3D reconstruction methods. And our category model generates plausible instance interpolations, and you can do few-shot reconstruction with just a few images plus this prior to reproduce the appearance of an entire category of objects. Next, I'd like to hand off to Kunhong, who's going to tell you about NeRFs.
Hi, my name is Kunhong Park, and I'll be presenting NeRFs, our work on capturing deformable scenes with neural radiance fields. Our work is a part of a line of research that tackles non-rigid 3D capture. There's a lot of great work out there on this topic, such as the ones I'm showing here. Existing methods can give you really great looking results, but to use these methods, you usually need an elaborate lab setup with multiple synchronized cameras and lights. We want to broaden the accessibility of 3D capturing technology by addressing the problem of casual capture. And by casual capture, we mean you should be able to capture something with a single smartphone camera and no special hardware. Once we have a video from a phone, we'd like to turn it into something you can render from any viewpoint, and perhaps get a nice estimate of the geometry while we're at it. So hey, I hear NeRFs are great at doing just that. So why don't we just train a NeRF? Unfortunately, NeRF only works on static scenes, and it fails catastrophically for moving ones. Let's take a look at a little visual explainer to understand why this is happening. The orange and blue boxes show two different moments in time. The cube in the middle flashes back and forth between a 3D rendering of each moment. If you look at the top right corner of the glasses, it's clear that the person's head is moved between the two observations. Remember that NeRF casts rays to optimize the scene. Since the subject is moving, these rays obviously won't intersect, meaning the NeRF won't get a coherent picture. Our solution to this is fairly simple. Just let the rays deform onto a canonical reference frame, which is shared between all moments in time. We deform the rays using a deformation field, which, much like NeRF itself, we encode within the weights of an MLP. This MLP takes a 3D point and maps it to a point on the reference NeRF. We also condition the MLP on a latent code so that it knows which moment in time it's rendering. When you're rendering the scene, you take a point along the ray and sample the canonical NeRF using the transformed points. Here's a simple diagram of how things come together. You take a point, transform it to a different point, and then render as usual. The previous slides are admittedly a bit of an oversimplification, since just mapping to the output coordinate directly wouldn't work very well. So how should we parameterize the deformation field? The most obvious idea is to have an XYZ displacement for each point. But let's take a look at a toy example to see why this might not be the best idea. Here we take a star and rotate it counterclockwise. Notice how the displacement at the edge of the rotation is much larger than the displacement towards the center. This makes a translation field hard to optimize since the network has to regress different parameters for the same transformation across points. So instead of just a translation, we parameterize deformation as a rigid transformation, allowing points to rotate as well as translate. And of course, the angle of rotation is the same for all points, meaning one parameter can explain the rotation for all points on the star. This example is 2D, but in 3D the intuition is the same. We just output parameters for rigid transformation, and now the network can predict a single set of parameters to rotate chunks of space. Here's an example of where the rigid transformation field shines. The translation field causes the book to get all squiggly since it can't take the whole book and move it. In contrast, the rigid transformation field moves the whole book and the straight edges are kept straight. Sometimes binocular input videos can be ambiguous. Here's an example of such a case, where the user tracks their head towards the camera. Inputs like this can cause heavy distortions, leading to implausible results. This reveals a potential problem with deformation fields. The optimization sometimes becomes under-constrained, since now the network can just move things around to satisfy photometric consistencies, rather than form a coherent geometry. That's why it can be beneficial to have some regularization. Thankfully, most motion in the real world is rigid, especially with people. Your head doesn't suddenly change in size. Here we'll introduce our elastic regularization scheme with a 2D example. Take f as any arbitrary 2D transformation. The Jacobian of this transformation, at a point P, gives you the best linear approximation of what is happening at P. We'll use something from the geometry playbook called as rigid as possible regularization, or elastic regularization, since the behavior resembles elastic materials. Essentially, you want to keep the transformation as close to a rotation as possible. This translates to penalizing any stretch in space. You can do this by keeping the singular values of the Jacobian as close to 1 as possible. So to actually compute the loss, you first take the singular value decomposition, or SVD, of the Jacobian, and penalize the deviation of the singular value matrix from the identity. We use a log here so that the contraction and expansion of the same factor get penalized equally. Here's what the optimization looks like with and without elastic regularization. You can see that we get a much more plausible deformation, and the user no longer looks deformed. An important detail I left out in the previous slides has to do with what we input into the MLPs. NeRF shows that instead of directly inputting the coordinates to an MLP, it's better to first encode it using a set of sinusoids with increasing frequency. The number of frequencies in this encoding controls the smoothness of the learned representation by tuning the bandwidth of an interpolating kernel as shown by Tansik et al. Here I show the interpolating kernels for various numbers of frequencies, and you can see that the kernels get narrower as there are more frequencies. The number of frequencies plays an important role and is at the center of a trade-off that we have to make. If we have too few frequencies, then we can't model the high frequency deformations, such as the slight smile in this example. On the other hand, if you crank up the number of frequencies, then the template overfits to an under-optimized deformation field, and here you can see that optimization wasn't able to turn the head correctly and converges to the wrong solution. Our solution is simple and echoes the common technique of course-defined optimization in computer graphics and vision. Rather than keep the number of frequencies fixed, we can slowly increase the influence of each frequency by sliding a window function. We define a parameter alpha that moves the window along the frequency bands, and this tunes the bandwidth of the kernel. This lets us use a smooth kernel, which is spatially coarse early on in training, and progressively make the kernel sharper to model high frequency details. You can see that by using this method, we can get the best of both worlds, and we can both get the slight smile and rotate the head correctly. Here's a video of the training progression with and without course-defined optimization. You can see that the convergence is a lot smoother with course-defined optimization than without. Now let's look at some results. Here we show rendered novel views on the left-hand side, and the corresponding median ray termination depth on the right-hand side. Although human capture is a key application of NeRFs, we can use it to reconstruct a variety of scenes. For example, the dog Toby, a badminton racket, a person standing up while drinking a cup of coffee, I think. I also want to quickly show off the quality of the geometry you can get out of these models. We got this point cloud by projecting the image pixels using the median ray termination depth shown in the earlier slides. One key limitation of NeRFs is that it can't handle topological changes, such as when I open and close my mouth here. Here's a peek at how our recent model, HyperNeRF, compares to NeRFs for topologically varying scenes. Thanks for listening, and please check out our projects and many other related works linked on this slide.
Hello everyone, my name is Zheshang Xu. I'm a research scientist at Adobe Research. In this part of the course, I will talk about relighting and general appearance acquisition problems in neural rendering. Here is the outline of my talk. I'll first present a brief overview of relighting and appearance acquisition, and then I'll introduce some of our recent works in this space which enable relighting and editing in volumetric neural rendering. And in the end, I'll briefly discuss some open challenges and opportunities in this field. In general, modeling the appearance of real scenes from captured images and rendering new images under new conditions is a central problem in computer graphics and computer vision. This has been studied for decades with extensive research work. An ideal model from appearance acquisition is expected to enable photorealistic rendering with changing viewpoints, changing lighting, and even flexible editing. Unlike pure view synthesis techniques that focus on reproducing the scene appearance under its original environment, appearance acquisition techniques generally seek to also change the scene appearance with specified conditions. And one core problem of it is to render a scene under a novel lighting condition, which is known as relighting. And a flexible appearance model would also enable other scene editing applications like material editing, shape editing, object insertion, and so on. In general, there are two types of method to do appearance acquisition and relighting. First, you can do a full reconstruction for your scene by reconstructing the geometry and material reflectance of the entire scene. And then you can render your scene with these components from any conditions you want. On the other hand, image-based methods are trying to avoid complete explicit reconstruction and instead directly output renderings from a black box function. This function is often known as a light transport function. Usually, image-based methods can generate photorealistic results, but it is very hard to edit the scene content they model. And reconstruction-based methods model explicit geometry and reflections components, which naturally allow for scene editing, but the rendered images are usually less realistic. Recently, neural network techniques have been applied on both types of methods. Now let's first talk about the image-based methods. We mainly discuss image-based relighting techniques, which generally consider a fixed viewpoint. And this image-based relighting problem is essentially to first capture some images of the scene under some lighting conditions, and then synthesize new images of the scene under novel lighting conditions. So you want to keep the scene content unchanged and only change the lighting in the image. Classically, this can be achieved using a sophisticated device called LightStage. And in 2000, Deformable et al. Present a seminal relighting work. They captured a lot of images under different lighting conditions using their LightStage, and then Relight images can be directly generated by linearly combining the captured images. The relighting results are very realistic, but they require more than 2,000 input images. So since then, various traditional and neural methods have been presented to improve the rendering quality and acquisition efficiency of image-based relighting. And early in 2015, Ren et al. Presented the first relighting work using neural networks. They distribute a lot of small MLPs in the image space and perform a per scene optimization of the MLPs on hundreds of the input images for relighting. This work, in fact, has many concepts that are similar to the recent works that use localized MLPs as an image or scene representation. In this work, as well as in all previous work, image-based relighting still focuses on per scene reconstruction with dense input images, which is very expensive. So to address this, in SIGGRAPH 2018, we proposed the first relighting technique that can generalize across scenes. We propose to use deep convolutional neural network to do relighting, and our network can relight a scene from only 5 input images, and it outputs a new image under any novel lighting condition as specified. So we can also linearly combine these relight images under different lighting conditions from the network to enable relighting under complex environment maps. Our method can synthesize photorealistic relighting results on diverse real scenes from only 5 captured images. It well reproduces the complex shading effects like the challenging specularities and soft shadows. And our work is the first deep CNN-based relighting technique. And we can also note that under a fixed viewpoint, the input and output of relighting is well aligned, and this is very suitable for applying convolutional neural networks. So since then, a lot of CNN-based relighting papers have been presented, and most of them focus on doing human relighting, especially portrait relighting. When doing portrait relighting, thanks to the strong category-specific priors, these CNN-based methods often handle lighting estimation jointly and do relighting from a single input image. In classical image-based relighting, the viewpoint is fixed as it stands in all these papers. And a more challenging problem is, can we also jointly change the viewpoint when do relighting? And one potential solution is to simply run view synthesis and relighting techniques in a sequence. And we in fact show this in our SIGGRAPH 2019 paper, where our view synthesis technique can be combined with our relighting technique and do novel view relighting from a sparse set of images captured under different lighting and viewpoints. And on the other hand, instead of doing relighting and view synthesis separately, recent papers have designed specific techniques for multi-view relighting. And these methods generally leverage a pre-computed mesh as geometric proxy to align the multi-view input images to a novel view, and use deep neural networks to learn the relighting function for any viewpoint. So in general, this can be seen as combining image-based rendering, image-based relighting, and neural networks for realistic neural rendering. And here we see that these relighting methods are still image-based, but they already leverage some level of geometry reconstruction. And as we discussed, another way of doing relighting and appearance acquisition is to do explicit reconstruction of scene geometry and reflectors. And there is also a lot of previous work in this reconstruction space. And recently, a lot of deep learning-based reflections acquisition methods have been presented, but they often consider only flat material samples without any complex geometry. Other papers study complete appearance acquisition with complex geometry, which is a more challenging task. In 2019, Kong et al. Proposed to use a neural network to drive the acquisition process of a specifically designed acquisition setup. And they can recover complex appearance and shape of real objects and do realistic view synthesis and relighting with very high quality. But this method requires using their designed special acquisition setup. And meanwhile, there are other works that are trying to use more simple acquisition setup. For example, our paper in SIGGRAPH Asia 2018, we with Zhengqin Li et al. Propose a learning-based approach to do full reconstruction from a single cell phone image with a turned-on flashlight. We leverage a cascaded unit to reconstruct the geometry as a depth map and a normal map, and reconstruct the per pixel diffuse albedo and roughness that express the spatially varying reflectance of the object. From this single view reconstruction, we can then do both relighting and view synthesis by simply rendering the reconstructed scene components. And our single view reconstruction method can already produce realistic images of diverse real objects. However, with a single view, we can only reconstruct a small part of the target scene. And later in a CVPR 2020 paper, we further present a multi-view BRDF reconstruction technique. We with Saibi et al. Present deep 3D capture, in which we first estimate per view geometry and BRDFs using a deep convolutional neural network, and then we fuse these per view estimates into a 3D mesh with per vertex BRDFs. And our method takes a sparse set of 6 images from 6 structured input views as input, and can output high quality geometry and reflectance that enable realistic rendering under novel lighting and viewpoints. And here I'm showing more results. Our approach can reconstruct various real objects and recover their challenging appearance with high specularities and complex novel variations. So basically, reconstruction methods are more flexible than image-based methods, and you can even edit the reconstruction and insert it into any scenes for graphics applications if you want. So in general, image-based methods and reconstruction methods both have some pros and cons. Reconstruction methods can be more flexible for more applications, but it is hard to achieve photorealistic rendering. And in general, one core challenge for reconstruction methods is that it is very difficult to jointly optimize geometry and reflections in rendering from end to end. Because they use meshes as geometry representation, which is classical, but is very hard to differentiate in rendering. And one way to overcome this is, in fact, to explore other neural representations that support simple differentiable rendering. And one promising direction is to use volumetric representations and apply differentiable remarching for rendering. So volume-based neural rendering can be done from pure view synthesis, as is shown in papers such as neural volumes and NeRF. And inspired by traditional reconstruction methods, we enable relighting for volume rendering in recent papers. In ECCV 2020, we propose deep reflectance volumes. We capture flash images with a cell phone, and we introduce a neural rendering approach that can achieve joint view synthesis and relighting using a novel relightable volume rendering technique. And later we combine this volume rendering with NeRF in the following work of neural reflectance fields, which further improves the rendering quality. And the core of our work is a physically based reflectance-aware remarking framework. And to introduce it, let's first review the remarking for view synthesis. For example, in NeRF, remarking is done by accumulating volume density and view-dependent colors of the sampled point along a ray. And this is written as an integral. Here, sigma is the volume density, c is the per point view-dependent color, d is the view direction, x is a point on the ray, and t is the volume transmittance on the ray at x, which is another integral that accumulates volume density on the ray. This representation is suitable for view synthesis, but it cannot support relighting because the appearance color information is all encoded in a single color function c that doesn't depend on any lighting information. And to enable relighting, we replace this function with a new one that explicitly takes lighting information as input. We consider a point light source illuminating the scene, and at each shading point on the camera ray, we mark an additional ray towards the light and consider the lighting information on the ray to compute the shading color at a point. At the heart of this shading computation is a reflectance model that can compute the reflected radiance at a shading point under any lighting and viewing direction. In addition, we multiply this reflectance term by the transmittance along the light ray that models the shadowing effect and also the lighting intensity at a point. So this as a whole leads to a physically based shading computation accounting for any arbitrary lighting and viewing directions. So instead of predicting view-dependent color as is in view synthesis works, our methods use neural networks to predict the reflectance properties at any spatial points. And to practically optimize such a network, we use a cell phone to capture flash images so that the light source is always co-located with the camera. And as a result, we can just mark one single ray to represent both the camera ray and the light ray to simplify the training. And after the optimization, our model can reproduce the appearance of flash images under any co-located lighting. And because we modeled reflectance in the volume that theoretically supports arbitrary lighting, we can then directly use the reconstruction to render images under any non-collocated lighting with complex shading effects like specularities and shadows. And in our ECCV 2020 paper, we used a deep 3D convolutional neural network to regress a discrete volume with paradoxical reflectance properties. And in the following neural reflectance fields, we combine our technique with NeRF that uses MLP and positional encodings. And this models a continuous volume leading to more accurate renderings with more high-frequency details. In a sense, our approach jointly reconstructs the scene geometry and reflectance in a fully end-to-end differentiable volume rendering process. We can therefore model scenes with complex shape and appearance and synthesize photorealistic images. In our method, a recovered neural reflectance field is essentially a renderable function that supports rendering under any lighting and viewing direction. This, in fact, is a model that functions similarly to the conventional 3D models represented by meshes and materials. And we thus can enable classical scene editing and modeling applications with our neural reconstruction. Here we show an example that we can compose a scene using the captured neural model of a real object and a traditional synthetic triangular mesh of the T-part, and render them under complex environment maps. These images are rendered using classical physically based path tracing with the standard rendering engine Mitsuba. And we can observe the interesting interreflections and shadowing effects between the captured real objects and the synthetic ones. So our approach, in fact, enables a full pipeline from practical scene acquisition to neural content generation to scene modeling and to final realistic, physically based monocolor rendering. This inspires incorporating neural scene reconstruction and rendering into the classical graphics modeling and rendering pipelines. So here we can see that by reconstructing volume reflectance, we enable relighting and also enable broader applications for neural rendering. But one remaining challenging problem is to do flexible editing of the volume appearance. In general, this is still very challenging for all neurovolumetric rendering techniques. For example, in NeRF, we can easily synthesize new images from captured images. But if we simply want to paint something on the body of this object, it is not doable. So in a recent CVPR 2021 paper, we with Fanbo Sheng et al. Proposed NewText, a neural texture mapping technique that can enable easy appearance editing. With this technique, we can paint this texture map onto the object surface in the volume representation and achieve consistent and realistic rendering. And we do so by disentangling the appearance of the scene from its geometry and represent the appearance in explicit, auto-discovered 2D texture space. And this technique can be combined with NeRF and also with neural reflectance fields to recover BRDF textures. Here are more results of NewText. Our approach can discover meaningful texture space and enable interesting surface appearance editing applications. So I have introduced some recent progress we have made in adding relightability and editability to neurovolumetric rendering. In the end, I'll briefly talk about some open challenges and opportunities in this direction. First, one key problem to think about is what is the optimal representation for relightable and editable appearance acquisition and rendering? Image-based representations can do relighting very well, but they are usually very hard to support more editing applications than just relighting. And the conventional representation of a mesh with BRDFs is the most widely used representation in rendering and can support flexible editing, but the reconstruction of it is still very challenging, and it is very hard to produce artifact-free photorealistic images from it, because it is very hard to create mesh in rendering in a differentiable way. Volume instead is a very promising representation, and it is much easier to use differentiable remarking to gradually optimize shape and appearance in a volume. And we have shown promising relighting and editing results using it. But there are still many open problems. For example, relighting a volume with accurate shadows and global illumination is very expensive and is much slower than rendering a mesh. There have been some recent works that are trying to address this. For example, the paper NeRF, and you will see some more details about this work in this course. On the other hand, most relighting works assume the lighting is known in the input. How to handle unknown lighting, especially unknown complex environment lighting, is a very challenging problem. Some recent papers address this to some extent, but in general, this is still a very challenging problem for not only volumetric relighting methods, but also other appearance acquisition techniques. In addition, there are also some other challenges in this field, like how to handle large-scale scene-level reconstruction and relighting, how to achieve more flexible editing and controlling on the neural representation we acquire, etc. While there are many challenges, neural rendering still opens up a lot of opportunities in computer graphics. We know that, in fact, without neural rendering, we already have a well-developed classic graphics pipeline of scene modeling and rendering that has been successfully running in gaming and movie industry for many years. So one way to make neural capture and rendering really useful in practice is to incorporate it into the classic graphics pipeline. And in our neural reflections fields, we show that a fully relightable neural capture technique can be used to generate 3D content that is naturally compatible with the classical 3D models and can be rendered in a standard rendering engine like Mitsuba. So this shows the opportunities of combining neural rendering with conventional graphics. On the other hand, we can also try to use advanced neural models to improve some traditional components in classical rendering. For example, in this year's SIGGRAPH, we with Kuznetsov et al. Proposed NewMap, in which we combine our knowledge in neural rendering with traditional material modeling. And we present a neural material model that can effectively model material appearance with complex microgeometry structures and enable efficient and realistic rendering of the material under any lighting and view interactions. So for more details about this work, please go to our talk. All right, so this is the end of my talk, and thanks for your attention and enjoy the rest of the course.